All right. Hello and welcome to this second episode of You Wouldn't Type Check a Car. It's been 1 week since we had the previous stream, and I think many of you actually went back and checked the video on YouTube and on Twitch. So thanks a lot for that. I hope all that content was really useful, and hopefully some of you would join us today again as we delve into this more technical stream today. As promised, today's stream is gonna be about CUDA programming. So not just any CUDA programming. I'm sure there's a lot of resources out there that folks must have read before and have written CUDA before. But I specifically want to focus on writing CUDA for sparse computations and optimizations that are focused around load balancing. There's a story about why I did this and why I'm interested in talking about it today. But before we get into like all the heavy duty stuff and while we are waiting for folks to join, I just want to like talk a little bit. So this last weekend, for the last 3 days, I was in Maine. I was on this retreat that my lab had organized, which was really fun. And I just returned a few hours ago. I haven't had enough sleep, which means I might be a little bit groggy, but hope that doesn't affect the stream in any way. I just want to since we are waiting for folks, before we start, maybe I'll just like show you guys some pictures of the place we were staying at and what we did there. So, oh, hold up, I just forgot to change the resolution. A second. Let's do this right now. Cool. Okay. Okay, yeah. So, just some pictures of where we were staying. So we basically had rented this really beautiful mansion almost with like 20 beds or something. Actually, there were more. We had rented two of them. There were like around 30 of us who had gone there. Only grad students, no professors. So it was a really fun time. Like the place was really beautiful. Like early morning, there was a lot of fog. There was a lake nearby. Really pretty. We did some kayaking on it. I don't have the pictures of kayaking with me because someone else took those pictures, but maybe I'll share them later. Yeah, it was a really good place. And then we had some bonfire and camping. Not camping, just bonfire at night, which was really fun. But yeah, that's what I was doing the last couple of days, and that's part of the reason why this stream is at a different time than the regular time. I would want to do this like on Sunday where most people can attend it, but because I was traveling this morning, we had to delay it. But okay, let's get it back into our discussions. If there are any questions, please feel free to ask them in the chat and we can go through them. So, a little bit about why this stream, a little bit about my relation to CUDA and sparse optimizations on CUDA. So I started my PhD in 2018, that is 5 years ago now. And when I started my PhD, I was obviously looking for a problem. I was looking for building a compiler for some new domain or writing some optimizations, starting out new. But while I was doing that, my advisor thought it would be useful for me to spend some time on the other project called Graphit, which is basically a DSL, or in our language, we call it domain specific language for graph applications. This domain specific language, Graphit, was written before I started my PhD. It was the senior grad student who was still at MIT was working on that project. But they were looking to expand the scope of that language and be able to generate code for GPUs. GPUs, as you know, are these massively packed parallel architectures, and these graph computations that they were trying to do were also really huge. So it made sense that you target GPUs out of it. And there's actually been a lot of research around this topic, targeting graph computations on GPUs, and they're hard. I'll get into why it is hard. But anyway, so I was thrown into this problem where I had never worked with graphs before, graph applications before. Obviously, in my data structures classes in undergrad, I had written BFS and I had written DFS and some other graph clustering algorithms and so on. But I had never written high performance graph applications. and I had never worked with GPUs. I mean, I knew what GPUs are. I had used a GPU for like used it as a device, but I had never actually programmed it as a GPU. And when I say GPU, I mean general purpose GPU. So using the device for not for rendering images or videos or all the classic applications of GPUs, but using it for some general computation. So I had never used GPUs. I had never actually written any CUDA code. So this was a new domain for me. I was not familiar with the hardware. I was not familiar with the graph applications itself, and I was planning to work on this. So what I ended up doing was spending almost 6 months, full 6 months, just trying to write optimized code for those applications by hand. I still have those repos around. Actually, let me pull it up. Maybe it should be here somewhere. Let me bump up the font a little bit. Yeah, so if you look at my early uh, here, I have basically around 30 different implementations of the same algorithm written in different optimizations. You can see SSSP written with like SSSP, TWC, Delta, Delta Kernel Fusion, Unfused, Fused, different variations of the same algorithm written with different optimizations baked into it. Oh, sorry, I realize I'm not sharing my screen. Yeah, so I was showing everyone how I was writing basically a bunch of different implementations of the same algorithm. So different BFS implementations, different page rank implementations, different SSSP implementations, connected component implementations. Just basically writing a lot of CUDA code by hand and seeing what works. This actually was a useful experience because I learned a lot more about GPUs. I don't know if I learned enough to write the most optimized code, but I definitely learned a lot about how GPUs work. And something I realized was GPUs are very different from CPUs. I mean, I have written optimized code for CPUs before, but optimizing for GPUs was an entirely different game. And part of it is because of the hardware features, part of it is because of the programming model, and part of it is just because I had very little intuition of like these massively parallel architectures. And I gained that over time, and we wrote the paper. That paper is was out to around 2.5 years ago. We also received the best paper award for that the year when we had submitted to CGO. And that paper talks about a lot of sort of compiler techniques to compile down graph applications for running them on these high performance GPUs. In fact, when it came out, we were sort of like the state of the art. Like the performance of our generated code was better than any other sort of related framework for a lot of applications. Not for all applications, for some of them, for some data sets. But anyway, uh, the point was I had spent a lot of time learning about GPUs, and I thought maybe I could share some of those kernel of knowledge with everyone here. Uh, the other thing about sparse computations, I mean, that was specifically graph, but sparse computation is obviously bigger than that. It is becoming relevant. It's becoming a lot more relevant again with all these machine learning models that essentially do these huge tensor computations or transformers, graph neural networks. These are really sparse applications, and they are becoming relevant as we sort of like creating these bigger and bigger AI models. We need the compute to support that. And if folks here are interested in like picking up jobs later that or are currently in jobs where they have to write these models, it would be maybe it would be useful for you to know how to write optimized code for GPUs and learn something from my experience. Again, this is a very limited scope thing, basically what I have done in my first 2 years of PhD. Uh, some of it might apply, some of it might not apply, but we'll see how it goes. Okay, so before any questions at this point, just about the background journey. I can talk more about it, but I can also talk about it while we do the development. Someone just please let me know if you guys can hear me in the chat. I know I've been speaking for a while. It would be really bad if you guys are not able to hear me, but I can see that my mic volume is positive. So I feel like you guys should be able to hear me. Yes, perfect. There is someone said they can hear me, so that's good. Hopefully, no audio issues this time. Um, okay, Let's talk about GPUs first. The two things to talk before we start writing code. One is what are GPUs and what makes them special, what makes them different from CPUs. And the other is what makes sparse computations different. I know this might be a lot of sort of repeat stuff for a bunch of people here, but I'm going to tie it into what we're going to optimize later. It's going to be related, so don't worry about it. I'm just going to share my iPad so I can draw stuff. Uh, Hold up, share screen. Okay, great. Okay, what makes GPUs special? GPUs, one thing you need to know is they are massively parallel. Oh, sorry, massively parallel. And when I say parallel, massively parallel, I mean on the order of 80 to like 100,000 threads. This is not typical of like your common CPUs where we have like 50 threads, 60 threads, maybe 200 threads, depending on how big of a CPU you buy. But GPUs are on a very different scale. Now, these 80,000 threads, whether there is the hardware to run all those threads at the same time, that's a different issue. But typically, when we spawn these processes, we are talking on the order of like thousands of tens of thousands of threads. The other most important thing you need to know about GPUs is that GPUs have very high memory bandwidth. High memory bandwidth. Why this is important is it supports different kind of applications. Normally, your CPUs have a main memory, and your CPUs have a chip where the compute happens. There is usually a bridge between these two where data can be transferred from the main memory or the RAM to the CPUs. This actually dictates a lot of performance. For memory-intensive applications, this can become bottleneck. Imagine simple case where you're rendering a lot of images. Those images are basically pixel data. There's a lot of triangles data that you're actually rendering and so on. This data needs to keep going back and forth between the CPU and the RAM. If you're constrained on the bandwidth, this becomes a bottleneck. This is because there are multiple types of bottleneck. There's like a bandwidth bottleneck. There could be a latency bottleneck. We'll talk about that later. But that was a problem for these video applications and these rendering applications. And that's why, like a very simple explanation why they created GPUs. GPUs have a lot of cores, but these cores are really small. What that means is these cores are not very complex like your CPU cores, like your Intel CPU cores. Think of them as like tiny cores basically that do not have any speculation, that do not have any out of order execution. Maybe the modern ones do have out of order execution, but they're simple cores. They don't have too much resources on the chip, but they have a lot of them. And the memory bandwidth is large, which means you can deal with a massive amount of data, stream it in, process it, send it back as you go. That's basically what you need to know about GPUs at a very, very high level. Uh, the way these threads are organized is also important, which means not all threads are like when you have a CPU, you have suppose 16 threads. All the 16 threads are almost the same, which means synchronizing two different threads. So let's suppose thread ID 1 and thread ID 2 would have the same cost as synchronizing say thread ID 4 and thread ID 5. But that's not true for GPUs. GPU threads are sort of organized in hierarchy, uh, and there are costs associated with sort of communication between those threads. That also tends to matter because we will see in those one of those load balancing optimizations how we get around those costs and how we actually make sure that the higher cost operations are done as few operations as possible. So let's talk about the GPU thread hierarchy. By the way, I'm going to talk about this hierarchy from the point of view of the software, from the programming model. I'm not getting into how exactly the hardware is laid out. So, like I said, we have these massively parallel. Let me actually just pull up the chat so I don't miss anything. Hold on. That's my chat box. Okay, yeah. So what I was saying is, actually, I can put. Okay, yeah. So what I was saying is, yeah, these threads, there's like massively parallel threads. Your threads are sort of organized in blocks. What that means is, suppose these are all your threads that are executing in your on your GPU or in launching your device code basically. I'm gonna show these threads as these lines. These are organized inside blocks. So the first level of hierarchy is blocks. Uh, block one, block two. Uh, the sort of what blocks are basically a bunch of threads, and usually the block size is somewhere between like 512 to 1000. So that's the degree of scale of each block. These blocks are sort of running on a single piece of hardware. That's the way to like sort of think about them to get a sense of the cost. But that's not exactly true. There's sort of details about how these threads in a block run. But the idea is they're running close to each other. Like on a hardware, they're running close to each other, which means the synchronization cost, they can be synchronized. First of all, they can be synchronized, which means you can say when a thread in a block is running, you can ask for it to wait for for all the other threads to reach this particular point. That's one way of synchronization. Or you could say you can exchange values between these threads without paying too much cost. That's the first hierarchy, which is blocks. So you have all your threads organized. Okay, the first hierarchy of thread is blocks. So block 1, block 2, block 3, block 4, block 5. These are suppose all the threads together are called the grid, by the way. So all your threads together is called the grid. The grid is divided into a bunch of blocks. And those blocks have roughly around like say 256 to 1000 threads depending on your launch parameters. It depends on how your resources are allocated basically. And then within these thread blocks, you have something called warps. Now warps are not technically a software construct, which means when you write CUDA code, you don't actually talk about warps. You don't say warp 1, warp 2. But it is such an important concept, like in the hardware, that you have to think about it when writing the software. So today, when we start actually implementing some of the code, we will actually talk about warps as if they are a real thing in the software. So each block is divided into sort of these warps. I'm demarcating them as squares because that's how we usually say warps are basically next to each other. So each block is divided into warps. What you need to know is each warp is always of the fixed size. So each warp always has 32 threads. Depending on your architecture, maybe this could be different. Like NVIDIA GPUs usually have a 32 warps per thread. Again, warps is also a NVIDIA terminology. I think AMD calls it something else, but the idea is similar. Each block is divided into a bunch of warps, and each warps has 32 threads. So if your block is of size 256, you would have a total of 8 warps in that block. And within each block, you have these warps. So within each warp, you have these threads. Now, what you need to know about these threads in a warp is that synchronization between them is super efficient. What that means is you can exchange values between these threads almost like a register and a register read or write. So normally in CPUs, when you read or write to a register, that operation is considered to be the fastest, right? Like in the hierarchy of memory operations, register accesses are the fastest. Warp shuffles or warp accesses to exchange value between threads is super fast. What you also need, the waiting for another thread in a warp is also similarly very fast. You could say, I want to wait to this execution point till all the threads in this warp have reached this point. That's also very fast. But there's downsides of this like this behavior of threads in a warp being very fast. What essentially happens is these threads in a warp are always running in a lockstep. That means they share resources in the hardware with each other. So usually if you think about CPUs have like a front end, they have a mid end or the back end where the execution happens, and the front end where the instructions are decoded. These threads in a warp share some of those resources, especially the front end and the control mechanism. So what this means is two threads in the same warp actually are running the same instruction at the same time. This is sort of a downside. So what could happen? Suppose for simplicity, let's say we have a warp with actually just four threads. Normally it's always going to be 32, but for the sake of simplicity, let's say it has four threads. Now, suppose this, and you have a simple program that say has operations like a equals to a plus 1, then you have b equals to b plus 1. All the just like normal CPUs, all the threads will execute the same instruction. So on the first cycle, suppose thread 1, thread 2, thread 3, thread 4, all of them will execute this operation. Now on the second cycle, all of them will execute the second operation. This is great. We are getting 4x the amount of work each cycle. Like normally, if it was one thread, you would just do one operation per second or per cycle. But now we are able to do 4x the more operations per cycle. But what this also means is if you have some sort of divergence in your execution. So I'm jumping a lot here, by the way. I'm jumping directly into like what the performance characteristics are, and I'm assuming a little bit about like how CPUs work or how modern architectures work. If you have any questions, please ask them. I'll try to elaborate more on what I mean by like cycles and what I mean by like front ends and back ends of CPUs and so on. But anyway, uh, what this means is like if the execution reaches a branch, so suppose you have a if C, and then inside that you have D equals to D plus 1, else E equals to E plus 1, suppose. God, I cannot write today. Yeah, so what happens in this case? All the threads reach this execution point, they all evaluate their condition, but at this point each could have evaluated the condition differently. These are threads, which means they have their own registers, they have their own sort of local state, which means they could all evaluate the condition differently based on what their parameters are. And some of them could take the true branch, some of them could take the false branch. But remember, execution can only continue in lockstep. They cannot, so half the threads cannot execute D equals to D plus 1, half cannot execute E equals to E plus 1. So what ends up happening is some of your threads get put to sleep. So suppose let's say the first two threads in this warp are executing the then branch. So only these two will execute and these two will go to sleep. Then once we reach the execution, once the then branch is done, these two threads go to sleep, and then these two threads will execute. And if there's some instructions after that, all of them will execute this together. So this is important. What essentially happened here is because we had some divergence, these threads had to be put to sleep, which means your resources are being underutilized. This is sort of like a first smell of a problem or what we need to keep in mind while writing program. What it essentially says is if your threads are not doing the same instructions or if the threads are not doing the same work, that leads to underutilization, which means your your cores are not being utilized properly. That's the first sort of input that we need to worry about. The second sort of performance metric or performance factor that comes in is how you access memory. So like I said before, GPUs have a very high memory bandwidth, but we also have a lot of threads, which means if you want to keep all your threads saturated, which means all your threads are sort of constantly doing memory operations or any operations in general, they are going to access a lot of memory. So even if the memory bandwidth is actually very high, if you completely utilize it, that will still be the bottleneck. So how you actually efficiently manage your memory is also important. There's a one sort of like general rule that comes in handy when talking about GPUs and memories, is that main memory accesses like the RAM accesses are expensive. There are sort of like, again, we talked about thread hierarchy. We'll talk about memory hierarchy next. But then there is like accessing memory from the main memory is expensive because it's off chip. You have to sort of send a request and then queue it, and the request is done. You bring it into the cache and then you read it and execute it. So off chip memory accesses are expensive. So what GPUs does to optimize that is it collects memory accesses from different threads in a warp. So for example, now for the same example with the 4 threads in a warp, suppose I have an operation where I'm doing, let's say x equals to a of I, okay, where I is thread I, some index that each thread has a different value. Now these are 4 different memory operations essentially, right? And we ideally want them to execute like this. We want them to happen at the same time. But what this leads to is 4 different memory accesses, like 4 different memory requests, because you are accessing 4 different memory locations. So in this cycle, we have 4 memory operation or 4 memory requests being sent. This puts a lot of stress on your memory bandwidth. If all imagine all your 80,000 threads constantly requesting memory 1 byte of data or one sort of like cache line every instruction, that's going to that's going to basically bottleneck your memory bandwidth. So how do they address this in GPUs? The GPUs basically have this hardware called memory coalescing hardware. So what that essentially does is if your memory accesses that are sort of close to each other or actually next to each other, it coalesces into a single uh, memory access or memory request. So suppose I had an operation like x equals to a of tid, where tid is like the thread id of that corresponding thread, which means first thread is accessing a of 0, second is accessing a of 1, a of 2, and a of 3, something like this, right? And so on and so forth. Now, when this hardware sees memory accesses like this, it says, okay, these accesses are right next to each other and they fit in the same cache line. So I don't actually have to make multiple memory requests. I'm going to just make a single memory request. This is what we call a coalesced access. And this is actually really performant. This makes your threads go faster because now your threads don't have to wait for the data to be fetched in the memory before starting the computation on them. Or they have to wait less longer for this computation to start. This is what we call coalesced memory accesses. And usually when we write GPU code, we try to maintain these coalesced memory accesses. Uh, so these are like the 2 sort of high level things you need to know about GPUs in the context of what we're going to talk today. There's more other things about GPUs which are very finicky, like there's registers and how do you do bank, like there's memory banks and how do you avoid bank conflicts, how do you do good synchronization. All those things will come up later. But for now, let's like focus on these 2 things. We want all our threads to in a warp to ideally be doing the same work at the same time so that we can sort of execute them in parallel. And second, we want them to access memory in a coalesced way. And coalesce is a very specific thing. It means it has to be right next to each other in the order of those threads. If I had changed this access to do A of 1, A of 3, A of 2, A of 0, these are also next to each other, but they're not coalesced because they're not in the exact order. These would lead to, I want to say, actually 4 different memory accesses. So that's not coalesced memory accesses. It's a very specific thing, which means your accesses need to be right next to each other. If that's the case, we get a lot of out of our memory bandwidth. Okay, so yeah, that's about GPUs. Uh, let's step a little bit into sparse computations. Actually, before we go into sparse computation, let's just write some GPU code and see how it runs. So the programming model. Any questions at this point, by the way? If I miss something, please bring them up in the chat. If something is not clear, I can explain it further. Cool. So I'm assuming no questions for now. Let's just get into writing a little bit of GPU code and see how it goes. So what I've done is, okay, correct me if I'm wrong, the branching was a problem because some older cards weren't designed to jump instructions in warp. That's not actually, that's maybe part of it, but what GPUs have is sort of, okay, so when you're trying to run sort of 80,000 threads or like 50,000 threads at a time, that requires a lot of area on the chip, right? Like the sort of transistors. So one of the trade-offs they make is they share resources. Like the decoding logic is shared between threads. in a war. So that, but because it's shared, it can only execute one, it can decode one instruction per cycle. Or yeah, so what that ends up meaning is, you, for your threads to sort of execute different instructions, some of them would have to wait. One would have to wait so that the front end reads the instruction, decodes it, and executes it, and then it can switch to doing the work for the other thread. But if they are doing the same set of instructions all across the war, then they are sharing a lot of resources, which is useful. So that's sort of fundamentally the reason why this control divergence is a problem. Uh, in modern architectures, in modern GPUs, like if you go towards like A100, H100, all the modern, very modern GPUs, they have addressed this problem to some extent. There is sort of like warp divergence can still be worked around. I haven't programmed for them, so I don't know how the performance characteristic changes exactly. But just from my sort of reading about the modern GPUs, they have addressed this problem in some way. But this, in general, like it's never going to be like CPUs. Your CPU threads can basically execute arbitrary instructions because they have all the resource. Like each thread, each core in the CPU has all the sort of separate resources. That's not the case for GPUs. So they have to share those resources, and that ends up meaning that if you do different instruction, that's a problem. The jump aspect actually is different. It's that uh, I think it comes in how you merge those threads, but I'm not sure. Maybe I can read up on it and talk about what happens when you have like sort of jumps in GPU code. But usually, what I talked about here was once the thread diverges, they sort of start executing different parts of the code, and one waits and the other finishes. You ideally want to merge them back again. So when you sort of reach f equals to f plus 1, where all threads are now doing the same thing, they have to be like actually merged again, and that doesn't happen automatically. The hardware cannot automatically figure out that that this thread is going to be merged with the other. So they basically then have to in the software insert these instructions to sort of merge them. Okay, interesting. For instance, on my laptop, Radeon GPU handling if-else block is done by a separate unit running parallel to ALU. Um, Sorry, I my chat doc is not showing up. Okay, here we go. So interesting. For instance, on my laptop Radeon GPU, handling of if-else blocks is done by a separate unit running parallel to ALU. Hence, branching is cheap on it. However, lack of availability of GPR could yield sometimes there is more contention for threads. Hence, high delay for threads even to enter if-else block. Uh, it's a separate unit. Yeah, I think maybe modern GPUs they might be doing different things. Yeah, I would like to. I'll read about it. Let me actually read about this later and get back to you. How AMD GPUs are handling branching these days. But anyway, going back to the original discussion, thread divergence is bad, and memory divergence is bad. Those are two sort of like guiding themes we'll use today. But before we sort of start optimizing the code, let's just write some code. Let's see how GPU programming works. So, oh, sorry. Yeah, so what I'm going to also do for today is I made this new repository. I'm going to share the, oh, wow. Yeah, I'll just pull it from my GitHub, I suppose. Hold up. Uh, yeah, so this is the repository for all the code I'll be writing today, and I'm going to put it into the resources doc that I made last week. So, CUDA optimization repo. Okay. So yeah, there's already some sort of utilities I have created. So for example, this has like a matrix loading code and so on. So I don't have to write this in the stream. So I've written this beforehand. There's sort of like a simple test case on how to load the graph, and if that works properly, some timing, hardness, and code. So we will we don't have to waste time writing that again and again. But anyway, so what we're going to do now is I'm just going to write a simple function that say okay, CUDA code, by the way, is you save it as .cu files just to differentiate them from CPP, but they are very similar. The languages, the CUDA as a language is an extension of C++. That's one way to put it. It's an entirely. Can you paste the link somewhere, please? Terminal is behind the whiteboard, so I can't see it. That is good. The better option is I'll just disable the whiteboard, and also the resources doc. Uh, I will put it in the chat, but for now, I'll just put a link for the repo in the chat. There's a separate resource doc we maintain for the entire stream, all the episodes, so we can go back to those later. But for now, I'll just share the repo with you. It doesn't have much. We'll be filling code into it, but yeah, you can look at it later. So let's start with the simple CUDA code. Like I said, these are massively parallel hardware, so let's make use of that. Let's not do something that's simple. So uh, it's okay. Like I was saying, CUDA is like normal C++ or C. It's an extension of those languages, which means they keep a lot of semantics of the existing language, and then they add more sort of features to it. So again, if you have written CUDA before, you should like you might know all these things already, but for now, just bear with me so that we can get started. So yeah, again, main functions like not like normal. Sorry, your standard headers and everything work properly. So I'm just going to uh, eventually have to print timers, and then I'll include my utils header that I created. Okay, so what we need, what I want to do is for the first sort of simple example is I want to create an array, a vector, and multiply each element by 2 and print it out. Okay, that's a simple thing we want to do. So normally how you would do this is you would say create an array of floating point values. So let's say vals, or let's say vector. Uh, yeah, equals new float, and let's keep it large, right? So let's define a hash, define vectors, vector size. Let's say for now, let's keep it 100,000. Okay. So I'm creating an array of floats, and I'm going to manually initialize with some values on the CPU. This code is running on the CPU, by the way. You'll see when we start going to the GPU. So now I'm going to do vector of I equals to I, suppose. Okay, it's the simplest operation. This code is normal CPU code. It runs on the CPU normally, like you run code. Now what I'm going to do is, for this to operate on this data, I need to first of all move this data on the GPU, which means I need to allocate memory on the GPU. Memory allocation on the GPU is very similar to memory allocation in C, where you have a malloc function that takes care of allocating, and sorry, you have a free function, so you have to do it manually. There are ways of, there's something you might have heard of, something called unified memory, which is a new feature in CUDA, but we won't be using that. Because in my experience, at least for the kind of applications that we do, it affects performance. It's not, it has its performance downside. So we will be manually managing memory for this episode at least. Okay, so what you need to do is first create a pointer. So I'm going to call it d underscore vector. By the way, for this entirety of the stream, I'm actually going to follow a convention where if a pointer is pointing to something on the host, I'm going to call it h underscore. If it's pointing to something on the device or the GPU, I'm going to call it d underscore. So let's clean that up. Now you allocate memory. The memory allocation is done using the function called CUDA malloc. It actually takes the address of the pointer that needs to be initialized. So it doesn't return a value, it takes the address of the pointer that needs to be filled with the value. And the second parameter it takes is the size of the size, how much memory you want to allocate. So I'm going to do size of d underscore vector into vec size, right? This is how you normally allocate a memory. The only thing you need to do is also cast this to void star star because it accepts it as the argument type is void star star. Okay, so this is going to allocate memory for our vector. Now we have to copy the data from the host. Just put some. Okay. I'm also going to, yeah. So now we need to copy the data from the host, from the CPU, into the GPU. What is bad about unified memory? So yeah, unified memory is great. Let me actually just quickly finish this copying part and then we'll talk about unified memory and why it's not as suitable for these sparse computations like you think they would be. So, okay. Now that we have allocated the GPU memory, we need to fill it up with the data that we just we created. So for that, we use the function CUDA memcopy, which is like a normal memcopy function. It takes the destination pointer. So I'm going to copy it to the device. I'm going to copy from the host. So this, and then it takes the size of how much you're going to copy. Sorry, it's been a long day. And then it takes another parameter, which is the direction of the copy. Are you copying from the host to the device or device to the host? There are better functions for it, but I just got used to it, so I use this. So I'm going to say CUDA memcopy host to device. Okay, this tells it that I'm copying from the host to device. This sort of like now the array is in the GPU memory. Now I need to sort of run this operation and I'm going to multiply each value by, say, a scalar. All the code that you want to run on a GPU needs to go into a separate function, which we call the kernel. So let's write that kernel for now. Kernels are annotated by these attributes, by the way. So if you add underscore global underscore to a function declaration, this is a GPU kernel which serves as an entry point for GPU code. If you have some other functions that are going to run on the GPU, you can mark them as device, which means they're also compiled for device, but a global one is basically an entry point into the GPU kernel. So let's call this vector scale because that's what we're going to do here. So we need to pass the pointer of the array that we want to double. So in this case, it's going to be d underscore vector. It's the same type. We also need to pass it a scalar. So let's say the scalar that we want to multiply it by it. Normally we'd also accept the size, but we know the size here. But anyway, let's just pass the size so we don't have to change the code later. Okay, so this is what we have accepted from the user. Now inside this, we want to do this in parallel because we are trying to sort of multiply different elements in the array at the same time. We can do them in parallel. There is no sort of dependence between these operations. It doesn't matter that we don't have to do them in a specific order. We can do them in any order. So what I'm going to simply do is I'm going to map each computation, each multiplication to a different thread. So now each thread needs to determine which element they are multiplying. And the way they determine that is by looking at their own thread ID. So the first thread will multiply the first element, the second thread will multiply the second element, and so on and so forth. So that first of all, we need to know the thread ID. So I'm going to make a variable called thread ID. And the way the thread ID is sort of computed is using these special variables that the GPU code has. So there are sort of three key variables you need to know. I'm going to put some comments and explain what they are. So the first is thread ID x.x. This is the ID of the thread within the block. So ID of the thread within the block. So within each block, there would be when I say block, I mean the blocks that we had talked about before. Like each grid has a bunch of blocks and each block has a bunch of threads. So this is an ID of the thread within that block. So each thread in the block will have ID like 0, 1, 2, 3, 4, 5. The next block again will have 0, 1, 2, 3, 4, 5, and so on and so forth. Then we have the thread, we have block dim.x, which says the size of the block. So this is the number of threads in each block that we are running. And then the final one we have is the block idx.x, which is the ID of the block in the grid. Again, many of you must have written this before, or if you don't, please feel free to ask questions. I can clarify. But these are basically three magic variables, you can think of them, that the CUDA programming model adds. That's the extension to C++, where you can basically ask the hardware what thread you're running on. Now, given these three variables, you can compute what the global thread ID is by simply doing this. Block ID x dot x multiplied by block dim dot x plus thread id x dot x, right? So multiply the size of the block by the ID of the block and then add the thread ID to it. So now we know each thread now knows, runs this by the way, and knows exactly what thread ID they are. So which element they're computing on. And now we can actually do the operation. So I'm going to say d underscore vector equals d underscore vector, oh sorry, d underscore vector of thread ID equals d underscore vector of thread ID times scalar, right? This is the simple operation we are doing. Uh, each thread does the simple operation and exits. That's great. Now we need to launch this kernel. What this means is we need to create a bunch of thread blocks and launch them. So the way we do that in CUDA is using a syntax. Okay, actually, first let's compute how many blocks we have and how many threads are there in each block. So I'm gonna say each block size equals to say 512, which is a typical size. We'll vary this depending on some applications, but for now, I'm gonna say each thread block is gonna have 512 number of threads. So how many such blocks do we need? So I'm gonna say num underscore blocks equals vec underscore size. We need to round it up. We need to round up the vec size divided by 512 so that we have enough threads for it. So this goes to that's a simple trick for rounding up, sort of a multiple, rounding up to the next multiple of a number is to add that number minus 1. So you can say 512 minus 1, if that's easier, and you divide by 512. So this gives you the multiple of sort of the not a multiple, like how many blocks you need so that you have enough to fit the vec size number of threads. And now I can launch the kernel. So launching a kernel is the same as calling a function. So I can say vector underscore scale first. Inside the parentheses, I send the parameters. So this is going to be d underscore vector. And then scalar, I'm going to say, let's say 4.2. And then I'm going to say the size, which is vec underscore size. But what I need to do is now specify how many threads and how many blocks I'm going to launch. That's done using the special syntax. So you start three angle brackets. The first is the number of blocks. So it just has num blocks. And the second is the size of the block. So I'm going to say block size. These are the grid launch parameters. So the first is how many blocks are there in each grid. And the second is how many threads are in each block. Now, at this point, if we have been following everything, this program is almost complete. Like we have allocated the memory, we have copied the data into it, we have written the kernel that does the multiplication, and we have launched it. But there is a small issue in that we rounded up the number of threads that we launch. We don't launch the exact number of threads. So there's going to be like some threads towards the end that should not do anything, which means they should not actually do this computation, because if they try to do this, then it's going to be out of memory access, out of bounds access, which we don't want. So to get around that, what we do is we do a simple check. We say if thread ID is greater than equal to vec size, return. So we're going to just like those threads will not do anything, they just return without doing computation. And this actually completes it. What I'm also going to do is I'm going to copy the data back so we can read it from the host. And that's done the same way. So you say h underscore vector, size of h underscore vector multiplied by vec underscore size, CUDA memcopy device to host this time. Sweet, and that's about it. So I'm going to save this, and I'm going to, actually I need to write the make file for this. I haven't written the make file. So I'm going to, let's say, build simple, also CUDA free. Yes, you need to CUDA free. We'll get to that. We're going to write more code and then I'll add CUDA free. So, but thanks for reminding. We don't want to leak memory. Although, just like CPUs, On CPUs, when your process exits, the memory is released. In the same way, on the GPU too, if you have any allocated memory and your process exits, the driver cleans up the memory. So don't worry about like your GPU just constantly, like every time you run the process, it will allocate some memory and it's constantly held on the GPU. When your process dies, it gets cleaned away. So I'm going to just write the same flags, actually, and I'm going to add, you know what, let's just do, okay. Uh, so we have some typecast error 39. What did I miss? I forgot the host pointer. Sorry, what to copy from. And there we go. So, by the way, there's a few things you need to know about compiling the GPU. So, if you look at normal, the way it's invoked, it's the compiler is called NVCC. So, its flags are very similar to your GCC, but this one also compiles like C++-ish CUDA code too. But anyway, so there are some extra flags that I have here. Use fast maths is a normal one. Max reg count is more of like a shed, like a input to the compiler to say don't use more than 64 registers per kernel. That's something I have sort of learned over years. And the most important argument that you need to know about is this gen code argument. What this tells the compiler is to compile this code for a specific generation of GPUs. So if you actually if you just Google the name of your, or if you look up the name of your GPU that you're using, you can find what architecture version they're using. So mine uses 80, so that's why I say gen code arch equals to compute underscore 80 and code equals to sm equals to 80. I'm actually, by the way, I'm using this one of the GPUs we have in our lab, which is Tesla 100. NVIDIA Tesla V100. It's a Volta generation GPU, so it's kind of old now, but it's still good. It's still good enough. And this uses compute capability 80, which is this version generation of the GPU. That's what we are compiling it for. Okay, so great. We ran make, it compiled it for us. Now launching this is just like running a normal program, something it's simple, and it ran completely. Nothing happened. We didn't print anything, but nothing crashed. So that's good. Let's just quickly also time this code just to see how far it takes. So what I've done already is uh, I've made this utility function actually run and time, which accepts sort of lambda. Uh, I'll talk about this quickly. And this takes how many runs you want to do and how many warm-up runs you want to do. So it's this function called so I just have this one function RV100 SM70. No, they are 80. At least I mean they might be different within them. My specific GPUs is SM80. Uh, yeah. Some of them are also compatible with each other. So sometime it should be fine. But yeah, like these ran. So yeah, these just take this function just accepts how many runs you want to do and how many warm-up runs you want to do. So yeah, let's also print this time. Sorry, it turns in milliseconds by the way. Okay, so we have some execution of 0.81 milliseconds, which is, I mean, it's kind of a lot, but it's also for 1,000 runs. But now let's just quickly scale up the vector size. Let's say instead of running it for 100,000, I'm going to run it for, say, uh, this is what, sorry, 10 million. And 10 million, I know my GPU can hold that much memory, so this should run. Ideally, you should check what CUDA malloc returns and see if it is null or not. Uh, and yeah, even with more number of threads, you can see that we managed to run it in the same amount of time. This is because uh, there's sort of like there's multiple factors here. One is that just because I increase the number of amount of work to do, it doesn't increase the execution time because you have more threads available, so it could run it. The other thing is there's also an upfront cost from just launching a kernel. Launching a kernel requires some constant amount of time. The operation that we are doing is very small, so that doesn't factor up. It doesn't show up into this. So that's why it's like 0.08 milliseconds, 86 milliseconds. But there are ways to further like sort of look at how much time each instruction took to. We'll get into that later when we start optimizing more code. But anyway, yeah, that's oops, sorry. Uh, this- yeah, so okay, now might be a good time to actually talk about unified memory and why not unified memory. So something we did in this code was call CUDA memcopy, right? Every time we wanted to move data between host and GPU, we call this CUDA memcopy function. This CUDA memcopy function eventually gets annoying because before you launch a kernel, you have to allocate memory, copy it into it. When you're done with the computation, move it back. This becomes annoying. So what NVIDIA came up in with an extension called Unified Memory, where the hardware manages memory for you. So while allocating memory, you allocate the memory as unified memory. So that memory basically has memory, actual physical memory on both the host and the GPU. And as you access it from either side, it moves the data between it. So it's based on paging. So like every time you have sort of like an access on the GPU, there's a page fault. It copies data from the host to the GPU, and then your kernel can directly access it. That way, you don't have to manually copy your data between back and forth. Uh, this obviously has the cost of paging, right? Like every time you have a page fault, you have to stop the execution, go to the host, copy it over, and then do it. uh, the problem with this is normally this is okay because you have sort of like you page in a lot of data, you're accessing data serially. That's great. You pay the cost of page faults very less often. But with irregular computations like sparse computations, you access memory all over the place. Like it's not going to be like I'm going to access memory location 1, 2, 3, 4. It's going to be like back and forth all over the place. That amplifies the cost of your page faults. You get a lot of page faults very quickly, which sort of floods your host's memory bandwidth, the PCI bandwidth, and then it's not great for performance. Like it ends up spending a lot of cycles in between your kernel when it should be running it. Uh, and that affects performance for sparse computations. I've seen that happen. It's not huge. It's in the order of like say 10%, maybe 10 to 15%, depending on your application. But sometimes that matters. Like the kind of optimizations we would be looking at actually give you performance improvements like say 20%, 30%, 50% if you're lucky. And in that case, paying these kind of 10% cost is annoying. So yeah, for all the optimizations we do today, we will not be using a unified memory. But all the sort of code that we write should still be the same. If you want to write sort of code that's like managing memory by itself, that should be fine. That's not the logic should still be the same. But yeah, hopefully that answers your question on why not unified memory. The cost just there is a cost, but it gets amplified when we talked about sparse computations. Okay, so this was a simple, just like a kernel of how to write a CUDA kernel. We will get, obviously, we'll see more of this today as we go. But what we have essentially written here is sort of a tensor operation. Let's annotate it here. What we have essentially done is in Einsam notation, we have done a of I equals to d times a of I. We this yeah, for each element in the array we have multiplied it by this constant scalar d. Let's actually use this. Yeah, a of I equals to d times a of I, or in vector, like in tensor notation, it's just a dot product, No, no, sorry, not dot product, just scaling the vector. The vector is scaled by constant. Yeah. So this, by the way, is an example of a regular computation or a dense computation. Why do I call this a regular or a dense computation? Is you can see the memory accesses that we have here are only dependent on thread values. Also, I mean, I'm going through the entire array and I'm going through each element in the array and performing a computation on it. Um, also, okay, first of all, I'm performing the computation for every element in the array. I'm not skipping over some of the elements in the array. And I'm doing them in a regular fashion, which means I'm doing 0, 1, 2, 3, 4, so forth, so on and so forth. This actually is called regular in this sense because uh, the access patterns are regular, but uh, sparse computations, when we get to them, they have irregular accesses. We'll talk about what happens there next. Okay, so this was a simple example of multiplying. We know how to run it, we know how to write it. So next up, what I'm going to do is I'm actually going to write sparse vector uh, scaling, which is exactly like this computation, but for sparse vectors. But before we start writing that, let's just whiteboard again and see what sparse vectors are and why they are hard. That is the sort of tricky part. Okay, so going back to the whiteboard, just going to see this, yeah. Um, what we just did is a dense vector scaling. So what are dense vectors? Dense vectors are basically vectors like these which have values in every element. So you have 1, 3, 5, 6, 7, 0, 5, 2. These are what we call dense vectors. So every element has some value and you're operating on them. Uh, the other what let's call this dense vector and let's call this sparse vector. A sparse vector is something that has most of its values 0. So you could have something like 1, 0, 0, 3, 0, 0, 4. This vector actually has only 3 of the elements as non-zeros and the other values are zeros. Now why is this important? We know that most operations on zeros have special behavior. So suppose I'm trying to sum up all the elements in a dense vector, I would have to go and add up all the elements. I would have to do 1 plus 3 plus 5 plus 6 plus 7 plus 5 plus 2. If I was trying to just sum up the sparse vector, I would just have to do 1 plus 3 plus 4. I can skip over those zeros because adding zeros does nothing. In the same way, for this dense sort of scaling of the vector, scaling a dense vector requires me to visit each and every element and scale it up and store it back. But in the sparse case, scaling up 0 doesn't do anything. Scaling up 0 is 0 multiplied by anything is 0. So I can actually scale them by going just visiting the non-zero elements and scaling them up. This actually brings up another sort of like optimization that's not for GPUs but in general, which is representation for sparse vectors. So you might say instead of storing these as these ones and 0, 0, 0, 0, 3, 0, 0, 4, I can just store the non-zero values. I can just store an array which just holds the values 1, 3, and 4, and these are just empty. But I also need to know where they are, so I'm just going to store another value which stores the location for each one of them. So this was at index 0, 1, 2, 3, 4, 5, 6. So this was at index 0, so it goes 0. This was at index 3, so that gets 3, and this was at index 6, so it gets 6. Does this make sense? This is sort of like a sparse representation of the same vector. We are storing the values in a separate array and we are storing the indices of where they are in a separate array. The benefit of this is one, it requires less memory. The two, it also accessing these elements is very quick. Not all operations, very few, some of the operations, but the basic idea is now if I need to go through all the non-zeros and say add them up or scale them up, I just have to go through the first array and I can do the operation. If I also need to know where they are, then I also need to go through the second array, but some operations become like very cheap. And that's what we are going to do. I mean, it's in a way these are exactly the same. Like if I write the code for scaling up a sparse vector, it's going to look exactly the same because it just have fewer elements. So we're going to do a different operation. Instead of doing sparse vector scaling, we are going to do sparse vector dense vector multiplication, SPVDV, which is basically A of I times B of I, C of I equals to A of times B of I. This is just multiplying two elements pointwise. But the idea here is this one is sparse, which we know that many of its elements are zero, and this B is going to be dense. So this has just a bunch of values. This sparse vector dense vector multiplication, and the output we're also going to store it in a dense vector. Uh, so that's the operation right now. Is this clear? I mean, I'm assuming if there's any questions, please let me know. And this, once we write the code for this, you'll realize where the issues come from. Where does the sort of irregularity in the access and the irregularity in the computation comes from? So I'm gonna hide this for a second, and let's start writing the code. Okay, so let's say source spvdb CUDA. What I'm going to do for this one is I'm going to copy over a bunch of code so that way I don't have to write it again and again. Let's see. Main function is almost the same. So this is going to be our dense vector. So I'm going to call this h underscore. Let's keep this h underscore vector. And we have allocated memory for it on the GPU. This will be rewritten. So let's forget that for now. Let's also allocate our sparse vector. So like I said, for sparse vector, we need two things. Hold up, let me stop sharing my screen. Yeah, for the sparse vector, we need two things. One is the list of the actual values, and the other thing we need is where they are in the array. So let's assume that this vector also has a size of 10 vex size. Let's actually bring this down a little bit first. Let's work with an array of 1000 for now. We'll scale it up later. Okay, so let's say this element also, this vector also has the same size. So it needs to, by the way, for doing pointwise multiplication, your vectors need to be of the same size. But I'm going to store this as sparse. So float h underscore sp underscore values equals to new float. I'm going to allocate an array of size vex size, but it doesn't need to be. This is the maximum number of elements that I'm holding. So I'm allocating the full size, but you probably need less. And then oh, sorry. And what do I do? And the second I need to know is it doesn't have to be a float. It has to be an integer. Or actually not integer. It has to be an unsigned integer. H underscore sp underscore idx. This is going to store where the indices are. Uh, and now what I'm going to do is going to first populate this array. So I don't really have a random way of generating these arrays. So I'm just going to fill every 100th element with a non-zero and or let's say every 20th element with a non-zero, and rest we can just leave them zero. So for int I equals to 0, I is less than vex size, I plus plus. We also need an int location equals to 0. Now I'm gonna say h underscore if yeah Actually, I should decide how many non-zeros I want to do. So let's say int nnz equals to vec underscore size divided by 20. Let's say because I'm doing every 20 element. So this goes up to number of nnz is short for number of non-zeros, by the way. We'll be using this again a lot. So I'm gonna say h underscore sp underscore values of I equals I, and I'm gonna do h underscore sp underscore idx equals to I times 20. Yeah. So every 20th element is we are storing I at that element. So it's going to be zero, a bunch of actually let's just do plus one, so we don't actually make it zero. Yeah. So we have one, then we have two at the 20th index, three at the 60th index, and so on and so forth. But we don't have to actually go through the uh, we only need to store the values contiguously. This should also have an I. Sorry, never. Yeah, so we are basically creating two arrays. The first array stores what the actual values are, and the second array stores where those values are located at. The corresponding indices match, by the way. So yeah, so we have these two. We have the sparse vector and we have the dense vector created. We also need to copy this to the GPU because we are operating on the GPU. This is where unified memory comes really handy, but we're not gonna be using unified memory. Sorry, t underscore sparse values equals to, and then t underscore sparse indices. And I'm gonna do CUDA. I'm gonna only do NNZs. We don't need the whole thing. Okay, so we have allocated the two arrays. I'm going to copy them now. Values. I could probably write some utility functions to manage data better, but I'm not going to do that for now. There we go. We have copied both the sparse array and the dense array into the GPU. And now we are going to actually write the kernel that does the pointwise multiplication of the elements and stores it in a third dense vector. Sorry, I forgot about the third dense vector. So let's allocate memory for that. H underscore D underscore, actually H underscore output, new float of X size. Underscore output. And this should be vex size because we are using a dense representation. Okay, so we have the input output arrays allocated. So I'm now going to write the kernel spvdv. I'm going to accept the dense vector first. Then I'm going to accept the two arrays. So b underscore sp underscore values and d underscore sp underscore idx. and then we accept the output. And I'm going to accept n and z and also vec size. Okay, so the code about identifying which thread we are on remains exactly the same. So we need to know what thread we are doing. But now here's what I'm going to do. We're having non-zero vals in h underscore sp value and contiguous when we allow coalesced accesses. They are. The sp values are stored contiguously. So if you can see here that this is actually being stored contiguously. Uh, Unless that's what you're suggesting. The values are stored contiguously next to each other. The indices are stored in a separate array, but logically there are zeros in the middle, which we're not storing. So yeah, values and h. Right, so now for doing pointwise multiplication, I'm going to, for each thread, I'm going to map that thread to the nth n and z. So if you think about it this way, if you're multiplying 0 by a particular element, that doesn't need to do any computation. 0 multiplied by something is always 0. So like we should also initialize the output memory, by the way, but we'll do that later. But the point is, for each thread, now I don't need to actually go over those zero values. I just need to go to the non-zero values and store them in the output. Everything else remains zero. So instead of iterating through the whole vec size, now I just need to iterate to the n and z's. I just need to go to the non-zeros. So what I'm going to do is for each non-zero, I'm going to first obtain the value. So it's going to be float val equals uh, d underscore sp values of d underscore sp underscore index, right? Sorry, my bad. Uh, I'm going to first obtain the nth non-zero, and then I'm going to obtain what index it is at. So float idx equals to d underscore sp underscore idx of thread id. So now we know where a particular non-zero is and what the value of that non-zero is. Now I need to sort of do the computation. So I'm going to say d underscore output of idx. Now I'm not doing thread ID. I'm doing IDX because so suppose the non-zero is at the location 3. I'm computing at the third location in the dense value. So it becomes d of output of IDX equals what's the vector? So it's here is d underscore vector, the dense vector in this case, also at IDX because it's also accessing that particular element in the dense vector multiplied by the value. So if you look at this now, this is a slightly modified version of the previous code, but instead of doing sort of a dense going through all the values in the array, we are only going through the non-zeros in the sparse vector and multiplying it with the corresponding element in the dense vector and storing it at the right position in the dense vector. So this is what we call sparse vector dense vector multiplication. Uh, let's just quickly compile. We also need to launch this. How many threads do we need, by the way, this time? We don't need threads equals to number of vec size. We only need thread equals to number of non-zeros because we are mapping one thread to one non-zero in your sparse vector. So the easy way to do the same computation as before, I'm going to compute the number of blocks. So in this case, it's going to be n and z. Instead of instead of launching non-zeros equals to number of uh, uh, the whole vector size, I'm going to only launch the number of threads for enough for the non-zeros, which means we should also out return if our thread ID is greater than number of non-zeros. So this will stop us from doing out of bounds accesses. And now I'm ready to launch the kernel. So spvdv. Uh, what are the parameters? Vectors, path values. Okay. zero exercise. Does this make sense? What we have done here, we have launched threads equals to number of non-zeros in the sparse vector, and then we are doing indexes into the dense array, and then doing the multiplication. So let's again, we need to update the map file. All right. I think I changed some header. So, oh, line 14 expression must have pointed to object type. What did I do? So, and 16, 50, 50. Expression must have integral on scope in and 50. I I have not been typing correctly today. Okay, yeah. So let's run this once and it runs properly. Let's also add the timing harness just so we know how long it takes to run. And there we go. So uh, okay, I'm also going to increase the vector size a little bit. Let's make it 100,000. There we go. It runs fine. We're able to execute it, but let's see what the issue is this time. We Yeah. So let's talk about irregularity now, or where does it come from in this computation? If you look at this operation where I'm trying to do C of I equals A of I times B of I, uh, uh, this this is C of I, but the I comes. If you actually simplify this, this becomes D underscore output of D underscore SP of IDX of thread ID equals D underscore vector of D underscore SP of IDX of thread ID times D underscore SP of values of thread ID. Now this is the problem. This indirect access is a problem. Remember we had talked about different threads. It would be great if they access memory next to each other. They are not doing that anymore. They are sort of like when indexing into the vector, they're making jumps because there's an indirect access. There's A of B of I kind of access. That's where the irregularity comes from. So this doesn't actually this is one of the bottlenecks that we'll have to look at. To actually see if this is an issue, let's actually profile this code. So I'll give you a few seconds to stare at this again. What I've only done is I've just constant propagated that IDX. I've just copied that code inside the bracket so you know exactly what is happening. And you can say that there's an A of B of I access, which means you have to load the index from the array first, and then use that index to index into the dense vectors. That A of B of I access actually is bad for performance. Uh, so next what I'm going to do is actually profile this code and see where the bottlenecks are. So normally I run this code like this, spvdb, right? So to profile this, what you can do is you can run it with this nice tool called NVVP, which is the NVIDIA Visual Profiler. Uh, for newer generations of GPUs, by the way, this is not available now. They have discontinued this. There's a new tool available, but because I'm using an older version of GPUs, this is the tool that we'll be using. But it's great. So dense vector access isn't contiguous, right? Yes, the dense vector access is not contiguous anymore because we're using the indices to access into it, so it's scattered into memory. We are doing scattered accesses, reads and writes both. Uh, so I did something wrong. Hold up. Okay, so what this software has done for us now? Let me see if I can zoom this in a little bit. No, it's only zooming in on the kernels. Hmm. Can you folks see at a higher level what is happening? Let's do this. Okay. Is this appearing okay on the screen on the stream? Hold up. Oh no, I've made a mistake. Oh, never mind. Oh, this window is very zoomed in. I can zoom in on the kernel, but I don't know how to zoom in on these. Anyway, we actually get into the instructions, and that will be clearer. So okay, so if you look at the whole timeline, we see that it launched our applications. They're sort of like CUDA malloc calls, which took a while to run, and there is the other sort of CUDA memcopy calls that took a while to run, and eventually there is our actual kernel that ran. So if you click on this, if I, yeah, this is the actual kernel. And also, what I'm going to do is I'm going to say examine GPU usage, and this will tell us, oops, uh, is my kernel not running? Okay, hold up. It's not finding my kernel. Okay, I'm gonna check if this has any errors. The easiest way to do that is a CUDA. Give me a second. I need to just quickly check why this is not running. Okay. Uh, Why not make safe malloc macros or CUDA malloc too? Yes, I should. I should make functions or macros for them. It's just I wanted to show how to write them, but yes, I should eventually make them. The point is, a lot of this code that I've written in the past is all generated by the compiler, so it never was an issue. Like we're always generating code for that and checking everything. But for the purpose of the stream, I should write a macro for it so that it takes a size, asserts that the value returned is not null and everything. So what I've done now is I've actually added a utility function called CUDA check last error. This is from one of the repositories that, I mean, my previous repository. So what this just does is just checks if the last kernel ran correctly, and if it ran correctly, if it doesn't run correctly, it just prints an error and exits. So what I'm going to do is I'm going to call this function after our kernel just to make sure that everything is running correctly. Uh, and I'm also going to just run once instead of running 1,000 times just to make sure everything is running correctly. Okay, let's see. Build. You know what? Uh, you might be right. I might have I might have forgotten what my V100's uh, compute capability is. Maybe it is actually 70. I was also programming for my local laptop before, which has a newer version of GPU. Maybe you weren't running this at all. Oh, there we go. Sorry about that. Whoever had pointed out in the chat that V100 is SM70, you were right. Sorry, I made a mistake because I was running the same code locally on my laptop and I modified it then and I forgot to bring it back. Okay, so now this time it's running properly, which means it wasn't running properly before, by the way. So sorry about that. Hopefully this time we should be able to see the kernel. Um, There we go. Here's our SPVDV kernel, which we ran. Uh, if I can, okay. So what I'm going to do is I'm hit examine GPU usage. That shows us how well the utilization was for all our kernels. I'm going to say examine individual kernels, and I'm going to select the kernel that I want to sort of examine again, and I'm going to say perform kernel analysis. This is a very basic analysis, but we can ask it to do more if needed. You can select this, and the first thing we're going to look at is global memory access pattern. So this is the one that will tell us how the memory accesses are. So there are two global memory accesses you can see here. This is assembly. This is called PTX, which is like uh, CUDA-ish assembly. Is it visible though? By the way, uh, the zoom level of this is kind of bad. Oh, I know how to do this. I'm going to add a window display instead of window capture. Okay, let's say the profiler, but obviously it doesn't want to capture. And okay, it doesn't want to capture that. Never mind. Back to display capture. Maybe I can zoom this in a little bit. I'm gonna crop this. Okay, this should help. Sorry, I'm still trying to figure out how to do this properly. Okay, is this better, easier to read now? Cropped a little bit. Okay. Yeah, so you can see that there are two instructions here, which are there's a load and a store. The load is on R6, which is computed using there's a IMAD, which is multiply and add, and that is where actually it's using R4, which is also loaded from memory. So the first thing it does is it loads from memory from R4, which is our load from the value from the index array. Then it uses that index to do a memory load from the dense vector and uses again that to store back. If you look at this sort of utilization, this memory coalesced access sort of graph, it shows the green is good. If this whole bar was green, that would mean that the whole access was coalesced. What this is saying is that it's not coalesced at all. In fact, if you look at the utilization on this one, you would see it's 31.6. So for each of the instruction, it has to do 31.6 memory accesses. Whereas in ideal case, it would have been 4 memory accesses. That's what it says. It says I had to do 31.8 memory accesses or 31.6 memory accesses, whereas I should ideally have done 4 memory accesses. Now, where does that 4 and 31 come from? The 4 comes from the fact that these are 4 byte values. So your cache lines are 64-bit, which means you can fit 16-bit, 16 byte values, 16 values together, and there are 32 threads. Uh, it should have been ideal 2, but it's ideal 4 for some reason. Anyway, so what essentially happening is we're doing 8x the more the accesses than we should be doing, which is bad. Just for comparison, let's actually do it with the simple case too. Let's run the profiler on the simple case. Uh, to see how that performs, how the memory accesses look like on that one. That also had a scaling memory access, right? Working directory is always wrong. Hold up. This is running over SSH, by the way, so I'm doing the display forwarding. That's why it's always annoying. Okay, next. Finish. Okay, so this time if I look at my compute kernel, one of them, I say examine GPU usage, individual kernels, and this time if I look at global memory access pattern, you can, okay, first of all it says analysis has completed and shows no issues. Uh, is there a way to look at the kernels? Yeah, it's basically saying that I couldn't find any issues. Um, like everything must be in the ideal case. It would have been nice if we could look at those graphs though. Unfortunately, it doesn't show because there is no issue. It's not showing anything. Uh, maybe memory statistics. Yeah, they should show something. Kernel have you examined? Okay. Unfortunately, because the accesses are all great, it doesn't show. Okay. Can you also share the previous disassembly of the function? How many GPRs in those registers does V100 have? We'll get to that just in a second. If you guys want to see the previous one, okay, this one is not showing anything, so I'm gonna close it. Unfortunately, there are no issues, so it doesn't want to show anything. Uh, yeah. Okay. Let's go one by one. So, how many GPRs general purpose registers does V100 have? That's a good question. I think it has a so the way registers are are assigned on GPUs is there are these hardware units called SMs or streaming multiprocessors, and each streaming multiprocessor has a bank of registers, which it shares with for all the threads. I think V100. Oh come on, V100 still has 65,000 registers in the register bank, but we can check it out. It's been a while. The last time I programmed this was a few years ago, so it's been a while. Uh, Somehow forgets what the working directory is every time. Uh, okay, there we go. This was the assembly that we were looking at before. So there's basically four loads, sorry, three loads. There's the load uh, on the values array. Then so this is the load on the index array. This is the load on the values array. This because R4 is being used inside this, so that's how I know that this is a load on the uh, index array. This is the load on the dense vector where I'm using the index to load the value. Then there's a multiplication fmul, and then there's a store on the output array using the same index R4. So yeah, it's if this helps, I can copy paste this in the resource doc maybe. That helps. Snippet assembly of the and I'm going to just quickly push this so you guys can see it right now. Okay. Yeah, I just added it to the resource doc. So if you go to my Twitch stream, you should, there's a link there. Uh, but if you go to my GitHub page and just search for CXX stream, uh, this repository, I'm going to drop the link in the chat. This has all the resources for the stream, by the way. So if you go to today's doc, it should have the PTX. And the bad instructions are these two. The last load and store is the bad one. Okay, so going back to the profiler, yeah, so these two instructions are the culprits. The global memory accesses are not happening in a coalesced way, which is causing our data to be the performance to be slow. So with this in mind, we're actually going to step into a little bit more of a complicated kernel, which is SPM-SPV. It has similar issues, which is basically sparse matrix dense vector multiplication. Uh, Hold up, let me just quickly bring back my display capture to the original. Yeah. Okay, so going back to our tablet, let's whiteboard this a little bit and then we can start writing code for it. All right, so let's talk about the next kernel, which is SPM-SPV, and how this also has similar sparsity issues, and also this has okay. So the kernel looks like this. We have C of I equals A of I of j times B of j. So here A is a two-dimensional matrix and B is a single rank vector and we are multiplying it. So we basically have a matrix, we have a vector, and we are doing a cross product between them, and we are getting a vector. Did I do this right? Yes. No, 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 no. I wrote it wrong. Dimensions don't match. Should be like this. Yeah, so this is C, this is A, this is B. We are doing a cross product between a matrix and... Oh, wait, this was not updating for some reason. Oh, seeing for the first time. Is this behaving weird? Is this getting cut? I'm gonna stop sharing and start sharing again. Okay, better this time. Yeah. So I'm doing a matrix vector product. And the idea is the same. I have a bunch of non-zeros here, and everything else is a zero. So all the empty boxes are zeros. And there are a few non-zeros that actually participate in the computation. And why does that matter? Because what we're doing with those values is I'm multiplying with b of j and summing up all those values into c of I. By the way, this is what we call Einstein notation or Einsum notation. This, if you write it as pseudocode, it basically means this: for I in the range, for j in the range, we are doing c of I plus equals a of I of j times b of j. So you can see that I'm summing over all those values. I'm not just multiplying and storing, I'm summing over the values after multiplying them. This means that if those value is 0, if this is 0, then this doesn't add anything, which means I can skip over the non-zeros. And that's where sort of the sparse optimizations come from. A of I of j times b of j sums up into c of I. This is the kernel we're going to try and optimize. And this is actually a very important kernel. It shows up everywhere. Sparse matrix dense vector multiplication. Uh, if you know about PageRank, the algorithm that initially Google used for ranking your pages, or even other sort of applications for the same, is essentially SPM SPV. So you basically SPMV, sorry, sparse matrix dense vector multiplication. Why is it SPMV? So if you think about this matrix, this essentially is the graph of computation that you have in PageRank when you're like when you assign sort of uh, where nodes on the in the graph are basically websites, and the edges between them are sort of edges on who is linking to whom. If you have that represented as a matrix like this, it's going to be a sparse matrix, because not every sort of website links to every other website. And then if you assign a rank to each of the rank, when I say rank, it's like a value for each website that can be stored as a single rank vector. And each time you can sort of propagate those ranks to their neighbors, which is what matrix vector multiplication does. When you do matrix vector multiplication, for each output website, you go and sum over the ranks or contributions from everyone who points to you. And that's so suppose website 1 here, website 2, website 3, and these are ranks for or old ranks for website 1, website 2, website 3, and so on. For each element, you take all the other websites that are neighboring it, and then you multiply it by their corresponding ranks and add it up. That's how you get the value. So basically you multiply this with this to give you the rank for each website. Now this matrix itself, this matrix is sparse because not every website is pointed to by other website, which means you only need to add up the ranks where there's an edge. And that's where the sparseness comes in. But the point I'm trying to get at is this has a lot of real world applications, and optimizing this has a lot of like value in it, because PageRank, like for example, Google doesn't run PageRank once; it runs PageRank every day, maybe like, or hundreds of times the kernel. The kernel doesn't run once. So every time, if you can improve the performance by even 10% or like 50%, you actually get huge gains out of it. Uh, so before I write the implementation, we will have to discuss how do we actually represent this matrix? How do we represent this sparse matrix? Normally, you would represent a matrix as a two-dimensional array, and you would store the non-zeros in it. But this is because it's a sparse matrix, so you want to have a similar way of representing this. One way that sort of a lot of scientists have come up with is called the CSR representation, or it's okay. CSR, or it's called compressed sparse row representation. What this means is your rows are compressed. So instead of storing all the values in the rows, only the non-zeros are stored. And the values in the row are compressed basically. So instead of storing this as a bunch of like a two-dimensional grid, it will be stored as like a set of rows where the non-zeros are sort of like stored together like this, depending on how many non-zeros it has, just like we had done with the vector. So they're sort of like collapsed into a set of rows with some non-zero values. This representation is very popular. I'm not going to get into why this is used and what benefits it has, but trust me, this is one of the most commonly used representation for sparse matrices. And that's what we're going to do. So conveniently, before I started the stream, what I've done is I have already written, oh, sorry, there's something. Shouldn't have. Uh, what I've done is I have already written, hide this window capture. Yeah. I've already written this matrix type, which basically has arrays to store a matrix like this. So it has basically two values, two integers. One is the number of rows. I'm assuming this matrix is square, by the way. So we don't have n by m, we only have n cross n matrix. So this matrix is n cross n, this vector is n, and this vector is n. For simplicity, this can be generalized to having n by m, but for now we're just going to use n cross n. So a number of rows and columns in this case. The number of values, so here it's the number of non-zero values only. We're not storing we only need to know how many total non-zeros there are. And then for each of those rows, I have this array. So the way CSR is represented is using three arrays. So first array is what we call the row PTR, row underscore PTR. Then we have the columns array, and then we have the values array. So if our matrix looks like this, so let's take a simple example of a 4 by 4 matrix, suppose. Okay, this has rows 0, 1, 2, 3, right? So this is gonna have an array of size 4, which is representing that array, and then we have the column indices. So let's first assign where the non-zeros are. So let's say the non-zeros are 3, 4, 5, 6, and say 8. So these are suppose the only non-zeros that we have in the matrix. The way this would be represented is these values are stored in the value array. So 8, 3, 5, 4, 6. So then the values array just stores where what the non-zeros are. The columns array stores what columns they are in. So this is 0, 1, 2, 3. So this is gonna be 2, 3 is going to be 1, 5 is going to be 3, 4 is going to be 2, and 6 is going to be 0. So these are storing which columns they are in, and for each row we're going to store where the non-zeros start. So the 0th row has its non-zeros here, right? The 0th row's non-zeros start at this location. The first row's non-zero starts at 3, so this goes here. The third row starts at here, and the last row starts here. Is this clear? These are basically storing where in the array do those non-zeros start. So this will be 0, this will be 1, this will be 3, and this will be 4. It's basically storing how many non-zeros are there basically in that row, as like where in the column array and the value array does the non-zero for that particular row start. I'm just gonna zoom in on this for a little bit. So we have 4 rows. That's why the row PTR has 4 values. Each row has can't see your board. Perfect. Yes, obviously I forgot to do that. Sorry, yeah, this is what I was talking about. So we have a 4 by 4 matrix which has elements 8, 3, 5, 4, 6. And I'm representing it as a compressed sparse row representation, which looks like this. So we have a row PTR which has so the size of this is number of rows. This is number of rows. The size of this is number of non-zeros, and the size of this is against number of non-zeros. The second is called the columns array, which stores which column those non-zeros are, and the final array is the values array, which actually stores the values. So 8, 3, 5, 4, 6 are stored in this array. The columns array stores which columns those non-zeros are in. So this isn't the 8 is in the column number 2, so 2 is stored here. 3 is in the column number 1, so it's stored here. 5 is in column number 2, so it's column number 3, so it's stored here. 4 is in column number 2, so it's stored here, and 6 is in column number 0, so it's stored here. And then the row pointer stores where do the non-zero for that row start and end. It basically just stores so row PTR 0 basically says my non-zero start from 2. Row number 2 says my non-zero start from the index 1 into the columns array. Row number 3 says my index starts from the third index in the values and the columns array, and the last one says it's at the fourth index in the columns array. As you can see, yeah, this just blew my mind. Yeah, it's a very popular data structure which is very efficient. Now you can see that the amount of storage required for representing this matrix went down from nr square to just nnz, or O of nnz plus nr. So originally, if you have a square matrix like this with n by n columns, the amount of space required this is non square. But for this representation, your required complexity is just nnz plus nr, because either could be bigger, O of nnz plus nr. And this is very efficient. If you look at typical graphs, so some of the graphs that we deal with has about like 100 million vertices and like a billion edges. If you try to score it as dense, it's gonna be what, like 100 million squared is 10 power 16. That is a lot of values to store. But NNZ is just a billion, which is 10 power 9. So you can bring down the storage a lot. That's first of it. The second benefit is iterating through these non-zeros is pretty easy. Like if I have to like sum up all those values, I just have to sum up this array. I don't have to go through the zeros. If I have to multiply some constant or if I have to do some operation on it, I have those indices and I have those values stored in a contiguous manner. But what is the downside for this? Doing those operation, you can already see that there's like a bunch of indirect accesses here. Like accessing the values for a particular row needs me to first index into this array, get the index and use that index to go into the values array. That's an indirect access already. The second indirect access is like show up from these column values. If you not if you need to sort of like index into a vector, you need to first take the value from the columns array and then use it in the length vector. That's where sort of other uh, indirect accesses come from. But we'll deal with that. We'll see how to sort of minimize the impact of those issues. So before I sort of like uh, yeah, so before I go further, I just want to like just talk about the implementation of this matrix data structure that we have done. In this case, what I've done is I've actually paired them together. So each array has a host pointer and a dense and a device pointer, and then we have the row pointer, which has the size number of elements, number of rows plus one. So what we also do is for ease, we also store the last index, which is in this case 5. So that tells us how many elements are per row. So this has usually of instead of having number of rows as the size, this has number of rows plus one. This is for ease of use later. Whenever we need to know how many elements there are, you can just do next. Like, if I want to know how many number of non-zeros are there in a particular row, like say for this row 1, I can subtract the index of the next one from this one. So I can subtract 3 minus 1, uh, uh, 3 minus 1, and that will give me 2. So I know there are 2 non-zeros here. But to be able to do that operation on the last one, I need to know sort of where does that row end, and that's what we store in the last element. So yeah, these values will all be number of rows plus one. Number of H columns and D columns will be number of non-zero. So this will be N and Z. Uh, and the values will also be N and Z because that's the number of non-zeros we are storing. And then I just have a graph loader that I borrowed from this project called GapBS. I'll drop a link for that too, since I'm borrowing its implementation. GapBS. Okay, here we go. GapBS is, by the way, a graph bench application benchmark suite, and they have a bunch of applications that, like graph applications and implementation, also have some data sets you can run that on, sort of test your implementation. It's a very popular benchmark suite. Hide board. Yeah, I was just dropping the link. Yeah. Oh, of course. I should be more careful with this. Sorry. So we have the row pointers, D row pointers, and the H column and D column. And this requires this. I just added the comments for the size of those arrays. So the H columns and the D columns and the H columns and the values arrays are N and Z size. And the row pointers are number of rows plus one. So I can store where those indices in the columns and the values arrays are stored. And then I just simply have a graph loader that because those are graph data sets, it's loading a graph, and then the matrix is stored in those arrays, copied into those what should I call it? The device buffers basically. This loader actually just loads from a binary format, but to populate it, I used the GapBS loader. So yeah. Okay. This should be it now. I'll start writing the code for the SPM SPV. Just give me a second. I need to check if I did this correctly. Hold on. What is happening? Just need to see if I loaded the graph properly before we run any experiments, otherwise we'll have issues. Okay, this looks correct. Stop sharing this. Okay, yeah, so we have our graph format defined. I'm gonna directly call the loader in a rest of the application so we can, this is a matrix format, by the way, so we're gonna use it as a sparse matrix representation. Okay, so let's add SPM SPV in a simple way where I'm going to call this sort of like the vertex map, a row mapping, where I'm going to assign each row that we are computing on to a different thread so we can perform the SVMV kernel. Okay, let's see. Source SPM SPV. So I'm just going to copy the function from here. Okay, we need the matrix name. We're just going to print out the number of vertices, and this can be fine. Okay, let's also allocate the vector. So we need uh, float. Uh, let's use better names this time. So let's say we are trying to do let's this matrix. Let's call it A. So that's like the capital A. Let's call the vector that we are, the computation we are doing is this, C of I equals plus equals A of I of j times B of j. Let's say this is the computation we are performing. So now let's allocate C equals new float of A dot num rows. It's a square matrix, so this is, and then this needs H underscore because Uh, next up, we have the, the device versions. So and this time I'm going to write a function that will do the allocation for us and test us, so we don't have issues. Let's write a function. Actually, let's write in the utils directory. Void underscore allocate. This can take a void star star ptr size t size, and it should be fine for now. So we can say CUDA malloc ptr size, and then we just call CUDA check last error. Actually, we don't need this. We just into a nicer function. Because the type doesn't matter, right? So we can allocate it as a char pointer and return the value. Next. Yeah, this is better. I'm just going to make a CUDA allocate function that we know always succeeds if it returns here. So we can now simply do CUDA allocate any rules times size. Okay, so now we have allocated our data. Let's fill it up with some initial values. So what I'm going to do this time is instead of filling some random values, I'm going to use a pattern that's very common, which is you fill up those values for each row. You fill up the vector with 1 divided by the number of non-zeros it has. That's basically in the page rank sense. That is initial values is like saying if every website had a rank of 1 or a value of 1, how much value does it push to its neighbors? So that's why it's like 1 divided by the number of neighbors it has. So I'm just going to quickly write the loop for that. This is going to run on the host. We could also run this on the GPU, but for now, let's just run it on the host. Uh, let's say a dot rows, because this is not an expensive operation. It's order of a number of rows, so that's why it's okay. First of all, we need to identify how many neighbors does this particular row has, or how many non-zeros this row has. So we say int degree equals, how do we compute that? We take the row pointers and we subtract the next row pointer from this row pointer. So where does the index for the next row start versus where does the index for this row start? We subtract that. So we say a dot d row ptrs of I plus 1 minus a dot d, sorry, not d host. We're going to use the host side buffer for this one. H underscore row ptrs of I. Now this gives us that degree, and now I can say d underscore b of I equals 1.0 divided by d. Let's blast this with sure. Okay, so yeah, we have initialized the array now, and now I'm going to copy it over. So CUDA copy uh, d underscore b. This should not be d. This should be h. You can't access device memory directly from the host. Okay, so we have copied over the data. Now let's write the actual kernel for doing sparse vector dense, sparse matrix dense vector multiplication. So how does that look like? Uh, SPMV. So I'm going to first accept the matrix T A. I'm going to accept the uh, load star D underscore B, and I'm going to accept the output array. So yeah. Don't need anything else. Sizes are part of the matrix A itself. By the way, here I'm passing the matrix by value, but that's okay because the matrix only has pointers inside it, which I'm going to use only the dense the device version. So that way, like I'm passing the matrix the structure by value, but that's okay. This is not copying the entire data. I just copying the pointers to the parameters. So okay, the first thing is always going to be getting the thread ID. That remains unchanged. And now we're going to also make sure that we're not accessing the row that doesn't exist. So if thread ID is greater than equals to a dot num rows, we return. This is clear. Now, what do? We want to say, okay, uh, for each row, we need to iterate to the non-zeros and sum up the values. But before we sum up the values, we need to, this is the output row, by the way. This is the row we are writing to. So we need to say, for this row, first initialize the value to be 0. So I'm going to say d underscore c of thread underscore id equals 0. Actually, no, we can't do this. Sorry, hold on. We are going to iterate the row of the matrices and then compute the value and store it. We're going to iterate the non-zeros in a particular row and store the output. So let's say int row ID equals to thread ID. Sorry. Uh, yeah, there's no trash. That one now. You can leave that trash. Thanks. So I'm going to say just RID equals to thread ID. Then for each of this, I'm going to iterate through all the non-zeros in this row. So how do I do that? In column, so I'm going to say column ID, PID equals to a dot row column ID x, not column ID. Column ID x equals to row PTR of I or of RID. CID x is less than a of row PTR of RID plus 1 because we want to go through all the non-zeros in this. And then I say CID x plus plus. Now inside this, first I'm going to get which column this value is. So this basically gives me, in the original one we had this, right? I'm going to copy this over again. So RID here roughly corresponds to I. Uh, yeah, and then we're going to get column ID next. So we're going to say COL equals to J. Okay, so let's compute what the column ID is. So UN32T COL equals to A dot, uh, so this should be B underscore. I call the D underscore H underscore columns and D underscore columns. So call, and then I also need the value. So I'm going to say float value equals to a dot b underscore values of column index. So I'm iterating through all the non-zeros in this particular row, getting the column it is in and the value it is in. So this is basically j. Now I just need to do the sum. So first I'm going to initialize it to 0. So I'm just going to say c of d underscore c of RID equals to 0. And then for each one of them, I'm going to say d underscore c of RID plus equals val, right? Val times d underscore b of col, right? So that is j. So I did this b of j, multiplied it by the value and added it to c of RID. And this does our basic version of SPM SPV. Uh, let's see if this runs properly. If there are any errors or anything, but yeah, we also need to launch it. Now, how many threads do I need? The number of threads I need is going to be equal to number of rows because I'm mapping each row to a different kernel. So let's see. I'm gonna keep the block size 5 and 2. That's okay. A of num rows. And I'm ready to launch the kernel. Let's also copy over the code that does the timing. So SPMV, number of blocks, block size. This is just going to be A, B, B underscore B. It's going to be B and D underscore H. No, D underscore C. Okay. Now we have our SPMV kernel ready. Hmm. Goodness. Oh, I named the file something here. Oh, I record SPM SPV. Sorry, I made a mistake. It's actually SPMV. The vector is not sparse. Okay. What does it say? Class matrix T has no member D row PTR. I think it's row PTRs. I call it. Yep, it's row PTRs. This is fine. Value of what initialized. This is C++, not C. So pointers don't implicitly convert in C, which is why we could have used templated version. But okay, anyway, so now we have our kernel compiled. This one takes a parameter, a data thing. So I have this uh, live journal dataset, which has a bunch of vertices and edges. Let's see how many. Yeah, so it has 4,084,847,571 rows, and the whole matrix has uh, this is what 85 million edges or 85 million non-zeros. So it's not an insanely huge matrix. It's a kind of a small matrix when it comes to typical matrix sizes, but it's 4.8 million rows and 85 million non-zeros. Just to give you a sense, if we had used a dense representation for this, uh, it would have been a huge number. Uh, it would have been something on the order of if we actually, let's see how much memory this would have taken us to store. So 4 bytes per float, and let's convert this is kilobytes, megabytes, gigabytes. It would have required us 87,000 gigabytes of memory to store this matrix, which obviously I don't have. 87 terabytes of memory, I unfortunately do not afford have. But with this new representation, which only requires me to store 12 bytes of, or depending on float or integer, only requires 8 bytes of data per edge. This actually comes down to uh, zero point 0.6 gigabytes of data. There's some overhead from the row pointers. I could say but that's not a lot. It's like some 4 megabytes of overhead from the edge data. So yeah, 0.63 megabyte gigabytes of data is enough to store this matrix. But there's also improvements in terms of performance, which we'll get to next. Okay, so we can run this matrix now. Let's just run the CUDA profiler and see what it thinks about our kernel. Uh, does it keep? Uh, doesn't show my kernel. Could it not run? Hmm. Uh, does run. Let's just do. There's also nvprof, by the way, which is a terminal version of the same program which prints. Yeah, it's not running. Sorry, the kernel is not running for some reason. Let me see what is happening. Oh yeah, okay, there is something wrong with the kernel. Let's see. This is fine. This is should be fine. Access a host array anywhere by accident. Okay, now it's a good exercise in also debugging it. So let's add -t, which is the CUDA equivalent of uh, running -g with your generative, see what is happening. Yeah, I'm just gonna attach CUDA GDB and see what's happening. User local CUDA. I think the problem is there's some error in the execution, which is why the kernel just crashes. The kernel doesn't run completely. That's the typical way of how it shows up when that kind of error happens. NV CUDA GDB. CUDA GDB is great, by the way. Works exactly like your normal GDB. Uh, Great for debugging like out of bounds accesses and everything. It's pretty good. Okay, so I'm just gonna say run and exits normally. Interesting. Did I add a return by accident? Uh, if thread ID is greater than equals to a dot num rows, this is fine. PTRs, t columns, t values. Oh, okay, no, this should be fine. Uh, Could also have initialized this, which I forgot, but that's not the reason why this is crashing. Okay, let's not do this inside. Let's see if that's part of the reason. Yeah, I know. No, it still doesn't run for some reason. So make sure that the last one is also running correctly. So I'm going to just change the condition a little bit. Nope, that is not the reason why this is failing. We loaded the matrix, right? Yeah. Okay, I think that R of CID is causing the BC of RID is causing the issue. It's here. This runs correctly. Am I right? No. What? Sorry, this shouldn't be happening. Zoom out a bit on the Vim, yes. Yeah, I'm just trying to figure out why the kernel doesn't run. It refuses to run for some reason. Uh, this time I'm running with the right architecture version. Uh, did I not allocate enough memory for this? I'm so confused. Okay, here's what I'm gonna do. I'm going to insert a breakpoint and we're going to debug this properly. Does not enter the execution. Do you think WSL2 is a good tool or Linux is it's better? Yeah, thanks for the question. We did cover that in the first sort of stream, and the gist is that I use I think they're both equally good. I have used standalone Linux enough before, and I have switched to WSL recently. WSL has gotten in a state that you can do almost everything you need to, including writing CUDA code if you wish to. The side benefit is that I also get to play games without having to switch between operating systems. So, yeah. Okay, let me quickly see what the issue is here. Wait, is the previous one running at least? Yeah, this one runs. I'm checking if I have enough. I should have enough memory. That's no, this is the reason, but it doesn't hurt to check. that is not an issue. Let's try a single thread. It's not. Okay, now it shows up. Great. So then, does it show up on num blocks? Is the blocks too big? Why does it repeat an error if that happens? Okay, it still runs. Okay, I think the block size is too much. We will debug why this is the reason. And why is it not complaining about it? The kernel launch failure. Size to be one, it runs. If I set it anything else, it doesn't run. I don't understand what is happening. Oh, it doesn't run again. Do you think passing an array might be an issue? Passing the array might be an issue. You mean passing the matrix as a structure? Uh, uh, okay, let's try dropping this parameter because I mean I've written code like this before. It should work, but you know what? Isn't hard to check. Let's just accept num rows. No, I think that's it ran once, so I don't think that's the issue. Does it consistently run at least? If I run it with one, okay, it does run consistently if I run it with one. And if I change it to 32, I think what's there was some warning with like CUDA profiler not able to gather the statistics because there wasn't enough memory. I think that's what is the issue. I don't think the issue is because of like our code being wrong. I think it's just that the profiler is not able to gather statistics because of uh, okay, see now it runs. Uh, let's go back. Uh, add this. I think I know what's happening. This doesn't need to be there. This doesn't need to be there. Let's see. Interesting. Yeah, this is what I need. I think this need to fix this. It's when I'm running the profiler, it's not able to gather the statistics because it doesn't have enough memory configured for the profiler. So let's fix that. This is probably like a new CUDA version issue that I haven't seen before. Size in megabytes. Okay. The default value is 8 megabytes. It should be a positive integer. I'm gonna do like uh, let's say like 100 megabytes and see how that fixes it. No, it's still not enough. Let's do more. I have 32 gigabytes of memory, so that should be enough. Uh, how much does it need? You know what? Let's just Google this. I've never seen this error before, by the way, so this is something new. I'm learning as we go. Okay, this is what I've done. It says illegal memory access. Am I doing illegal memory access? I'm not even doing an access. I'm just doing RID. CUDA has a print F2, by the way. Uh, see what is even it running? Shahada. Probably there's some uninitialized memory which is causing issue. I think it runs. The kernel is not running. Okay. Can't see a check. By the way. Check PTX. I can check the PTX, but let's see. Okay. User local CUDA. It has this thing called CUDA obj dump, which is the same as obj dump. Uh, CU obj dump. Let's see what this has. SPMV. It's not. Just flag for this extract PTX. Shell. Oh, Interesting. And dump PTX. Okay, let's try. No, it doesn't. What? Sorry, I this has changed. Something has changed. Okay, CUDA 11 dump PTX non-binary. Sorry. Oh God, this is the whole manual. Uh, cool. OPJ dump. Except group in files. Give me a second. Oh, I think I need a source. Nope. Dump says. Okay, there we go. Sorry, this took a while. Uh, who wants? Okay. Um, there is. Uh, you can upload the VOD. Yes, I'm gonna upload the VOD. If you need to hop off, that should be fine. Yeah. This took longer than I had imagined. Okay, so we have a bunch of moves. Uh, those register moves are usually for the third ID computation. That's what I'm guessing. There's a load 64 on C. Read loads. This is not the SPMV kernel. Something else, is it? No, this is SPVDV. Okay, this is a different thing. We're looking at SPMV. Here we go. Uh, so why is this function so long? Let's try it the way you suggested. Uh, okay, here we go. Okay, so this easier. We have the register moves for reading the thread ID, then this computes the multiply and add to get the thread ID. There's a branch to check if it is less than parameter 1. If not, goes to the exit block, that's fine. This one is not, there's a store at the end, which I'm confused about. Yeah, this is the store that we want, right? Yeah. So we have Kernel looks fine to me. I'm not sure why this is a problem. This is doing a multiply and add to compute the index on it, and just stores RD4. RD4 is 4 times R1. 4 times R1 is stored in RD3. Add RD2 to it, which is our index, and store 0 there. Like, this is a fine. The kernel looks fine to me. I don't think this is even the issue. This is all it's doing. But don't load the graph. Very good. That's all I need, right? I also need these. Sorry, this is annoying. Trying to isolate where the issue is. SPMV kernel does run this time, and it does print RID equals to 0, which is good. If I run one kernel, what happens if I run 32 threads? It does run 32 threads. That's good. What if I run block size number of threads? Let's run threads. Single blocks. Then what goes wrong? Oh, I think if I load the matrix. Okay, something is wrong with the number of rows. Uh, when launch a large number of blocks, it fails for some reason. Uh, you know what I'm gonna do? I'm going to quickly try something. I have recently installed CUDA 11, but I also have CUDA 10. I'm going to check if this is an issue. 10.1. Its origin was its version later than 8 and not amazing. Do I have an old version of GCC? GCC 10, 11.4. Okay, yes, Rans. I think there is something wrong with my CUDA version. I don't know what, but I think it's an issue with the profiler. I don't think it's an issue with the code itself. Let's keep it this way. Let's take this as, let's try it this way. Okay, here's what I'm going to do. I'm going to change this code a little bit. Oh God, why is this so hard? Instead of launching more blocks, which I don't know why is it wrong, a dot num rows plus block size minus 1 divided by block size. I'm just, hold on, let me, num rows. Find it. Oh, matrix T has no block size. That's one block size, sorry. Never mind. Let's see what kernel launch parameters we are doing. Maybe I'm launching too many blocks and that's not supported. I might have made a mistake here. Okay, 5 and 2 boxes. Okay, number of blocks. Here's what I'm going to do. I'm going to launch a fixed number of blocks, and inside that, I'm going to loop through the more number of blocks required. So that's an easy way to fix this issue. What I'm going to do is I'm going to take num blocks as a parameter. This is 2 now. Uh, and inside this kernel, I'm going to do for b int pid equals to block id x dot x. Pid is less than num blocks pid plus plus. And inside these, then I'm going to use the sort of virtual block ID, which comes down here. Yeah. Uh, use the PID, and I'm going to sync all the threads at the end. So this instead of return should just do to return. And then I'm going to take. So this is basically now simulating more blocks on fixed number of blocks, and we will see if this fixes our issue. This shouldn't be happening, but okay, it's launching our kernel at least. Uh, 160 we should be able to launch. Okay, I'm going to see if the whole kernel runs now with all our code. Okay, last go. The kernel stops working. Is any of this causing the issue? Okay, running this loop is causing the issue. Okay, this might be a separate issue. This might just be us, me doing some indirect access, wrong access. The D-row PTRs are allocated with the right size. Let's go here. And I have asserted properly that they are not empty. The D-row PTRs have been copied from the H-row PTRs. It's good. Okay, I think this is the problem. Maybe this is an out of bound access for the last one. If I didn't allocate enough memory, this could be happening. Let's see. Uh, let's just do. Nope. Okay. And now the loop is empty, so I guess it just gets optimized out. Yeah, that's not the problem. Also try this. CUDA. different GPU. It still doesn't help. I have a bunch of GPUs, so I should be able to run on something else. But it doesn't crash. Uh, I'm going to see if the computation at least runs or not. That's a large, nasty thing. Hmm. That's a lot of garbage values, so the kernel did not run. Uh, is this? Okay, this time it is all initialized to zero. So when I run the kernel, does it end up corrupting some values? Yeah, it corrupts those values for some reason. I don't know why. All I'm doing inside the kernel is C of RID equals 1. Oh, and I'm also doing this, sorry. Maybe this is running correctly then. Um, okay, yeah, this is running correctly. Just have to make sure everything is running. The profiler, we can look at it later. Uh, let's see. We should compute the value on the host correctly and see if they match. Okay, I'm going to complete a compute a reference value and see if they match. I think the profile is not showing it. Maybe it is running. Who knows what is happening? Just I'm going to click. Okay, this should be good. Now I'm going to compare those values. Floating points. I should. Let's see. Um, oh, I'm smelling some weird floating point integer conversion. It could be that. I'm not able to see what is happening. Okay, there is a bunch of minor mismatches. No, there is huge mismatches. Did I actually puts the gun? Yeah, I did the whole thing correctly. I'm going to remove this for now. If this is nothing, there is the. Okay, there isn't too much mismatch now. There's only one mismatch. And where is that? Oh, yeah, okay, perfect. This is happening because I did not compute the last row. I think our kernel was just running fine. It was just the profiler wasn't showing anything because some resource constraint. This is. Oh, I should have run the old version of CUDA. Okay, there we go. It runs properly. I wasted an entire hour trying to debug an issue that doesn't exist. Oh, God. Okay. So, for folks who have been following what I've been trying to do, I try to just not run the profiler and just check if the output matches. And the output does match. I made sure that the reference output matches the one that the CUDA is computing, and that seems to match now. What happens if I do? Uh, does it still match if I run the profiler? It does match, and this time it also runs. I Some weird randomness to this, which I can't seem to understand why. This if Okay, we have a working implementation. I'm going to go ahead with that for now. We have stuff to optimize. Okay, we have uh, code to actually make sure that the output that we're getting is correct now. Uh, yeah, and just to show that this is actually working, if I introduce an error like this, like say something like this, it should show up that something is wrong. If I think it would. No, okay, yeah, there is a bunch of mismatch, which means that our code is running correctly. Oh God, okay. If I go back and look at the recording, I'll see if I can find if I did something wrong, which I inverted, like I fixed accidentally, and now it's working because now the kernel seems to run. Let's go back to the profiler and see what the uh, profiler says about our code. We have those indirect accesses, by the way, which we have to work on. Okay, yeah, our kernel is running this time. I'm gonna do examine GPU usage. It'll tell us how good or bad our GPU usage was. So examine kernels and yeah, let's look at utilization. Yeah. So the first thing I'm going to look at this time is not actually memory coalesced accesses. We know that memory coalesced access our accesses are going to be bad because we have indirect accesses. But this time I'm actually interested in looking at how well did we utilize our GPUs. Let me focus on this one. Yeah, so if you look at our kernel now, I'm doing a compute utilization uh, profiling, and if I double click this, okay, so here it is. Low compute utilization. If I hit more, it basically says that the multiprocessors of one or more GPUs are mostly idle. So we have a utilization of 5.5%, uh, which is bad. Like, is it specifically for this kernel? Okay, let's look at divergent execution. So what we saw was that the kernel doesn't have good utilization, which means many of our threads are sitting idle. So let's peer into what exactly is actually we compile it with dash g, which is also not good. The fact that we are able to see the source code means that we are running it in debug mode. So I'm going to cancel this and I'm going to run it without debug symbols just to make it run properly, fast enough. There's some comments. I use CUDA 11 for most of my application. Maybe upgrade would work. I used to use even lower CUDA version. I used to use 10.4 before, and that used to work fine. I think this is some driver like CUDA mismatch issue, maybe. Uh, let's see if at least, okay, there's a mismatch starting. Just by removing dash G, there is a mismatch now. But it's minor. I think that could just be fast math. Yeah, yeah, okay. So okay, we're gonna fix this. This is not an actual issue. What this is basically saying is that the difference between if it's floating point, right? The difference between them two is too large. That also shows up an issue. So what I'm going to do is I'm going to say if the difference between them is greater than 0.0.1 f, then complain. Otherwise, don't. Oh, sorry. I need to make absolute value. Uh, C++ load ABS. I just study ABS, right? Yeah. Yeah, if the absolute value of the difference is more than 0.0001, then we are going to say that this is a mismatch. Yeah, is that too much of a difference? How much is this? 82135. I'm going to reduce the error. This is standard, by the way. We always compare like correctness by checking the difference between floating point values. This is or difference being larger than 3 epsilon, then mismatch. Yeah, we could do 3 some percentage of the value too because it's floating point. That's how it works. Uh, I think this is fine though. Uh, let's say it's 0. Let's say if it's more than 0.1% of the actual reference value. Uh, yeah, let's say 0. F of I. Yeah, if the difference is more than 0.1%, then we will compare. It's also computed on CPU versus GPU, which have different architecture, so the value sometimes differ. Okay, so this at least, okay, we know that it's running properly, and it's running fast enough. So user local CUDA open. Let's do the analysis on how good or bad it's performing. The point I'm trying to get at with this time is that there's going to be divergence, but yeah. Okay, so again, the same thing. We have a low kernel utilization, uh, but let's look at individual kernels. Yeah, it still says that the most of the GPUs were idle. So 2.3% utilization is what we have. And if you look at divergent executions, we can see where does the execution divert and why does it have to sit idle. So we have a 19.2% divergence, and all that divergence is happening in this loop. So okay, so here's the thing. This red bar that it shows, it basically shows where the threads have differed in the execution. Uh, yeah, again, it's the same as before. It's long. The more red it is, the worse it is. And the point where it shows that the divergence is happening is at the branch in the loop that goes back. So in our original code, if we look at this, uh, if we no, if you look at our original code, we have a loop at the end, right, which goes over the number of non-zeros in each of the rows of the matrix, and then does the computation on that. What ends up happening is because different rows have different number of non-zeros, those non the time taken to compute those is different, which means different threads will run different number of iterations of that inner loop, which is where the divergence comes from. So suppose one of the row has 5 non-zeros and another row has 100 non-zeros. The problem is, while it is doing 100 and say 1000 non-zeros and say 5 non-zeros, while it is doing those 1000 iterations, the other threads which only has 5 is sitting idle. It has nothing to do. And this actually is one of the key issues that I was trying to get at from the beginning of this of the stream, which is load balancing. This one shows that there is a load imbalance in the computations, and that's why our performance is trash. It's basically saying 2.3% utilization of our GPU, and we could definitely do better than that. If you look at the execution time, that's like one iteration is taking 0.36 milliseconds, and I know from my previous code that I can optimize this much more. Like there is enough room from improvement on this particular graph for SPMV. So why is this happening? It's because of load imbalance. So now, why does this load imbalance matter more for GPUs than CPUs? Well, there's two answers for it actually. One is that you have a lot more threads. When you have a lot more threads, any sort of like disbalance. So okay, this particular graph data set that I'm doing the computation on is actually what has something called a power law distribution, which means that a large number of vertices have a very small number of neighbors, and few vertices have a large number of neighbors. An example of that kind of graph shows up in, like, say, social networks. Like say you have a bunch of Twitter followers. Very few people have an extremely large number of followers, and then large number of people have few followers. So that kind of distribution actually creates a lot of load imbalance. Like when you're processing those vertices or those rows that have a lot more non-zeros, it sort of locks the processor and anyone else is waiting. And because you have these larger number of processors, like 80,000 in our case, you are waiting for a lot of your threads are waiting because your data is not properly distributed. The other issue is that these processors are very weak. They don't like do any fancy sort of like synchronization, or there's no like fine-grained thread mapping to hardware, which means the hardware doesn't sort of take care of load balancing between the actual running cores. And because of that, it ends up uh, like stalling basically, and that's where the utilization goes down. If we again that's part of the reason why our performance is bad. The second reason, let's look at our global memory accesses. Let's see if those are good. So we have a bunch of global memory accesses, and some of them are in the ideal range. Some are like this one has 5:4. So this one, like, it says it should be ideally 4, but it's 5. So that's not too bad. But the other ones we have like 1.5, and 1.5 ideal accesses, but it's actually 6.4, which is really bad. So like these ones, the green shows like how much of it is ideal, and the red one shows which is like how much of them are not ideal. So yeah, these loads, if you look at all of them, they are inside the loop. So they are when we are loading the data for each edge, as we're going through the non-zero in the matrix, we are loading those values, and we're loading those column indices, and then we're using those column indices to access into the vector for the store and the load, and that is where the performance is actually very trash. So if you see, there is a load here, which is actually, and there's a store here. These two are pretty bad. So yeah, we would have to fix these. What about these? Why are these bad? These are actually accessing memory one after the other, right? Like we are accessing edge data consecutively. The problem is different threads in the warp are still accessing faraway regions, because each sort of thread in the warp is working on a different vertex, which means they're accessing far away memory locations, and that's causing our like global memory accesses to be pretty bad. So there are like multiple sort of strategies we can use to improve these one by one, but we know where the issues are. So for first, we're gonna try to make those accesses coalesced. So instead of each thread handling one vertex and then doing all its edges, we're going to make the warps themselves handle a set of basically a set of threads handle this entire vertex. So let me draw this one and maybe it will be clearer. Um, yeah, this is the part of the stream, by the way, which where I wanted all the technical discussions to start. So uh, we finally got there, but we only have half an hour left now. So I will try to make it into a good discussion at least, and then we leave at a point where we can pick up again. I wasn't expecting this to be so bad. Oh, where's my Zoom now? I also see some binary search implementation. So would love to see how branching effects would pan out on V100 with your upper bound code. That actually is that helper utility for binary search. We actually use it for load balancing in the middle of the kernel. So when you're trying to balance the number of non-zeros to be processed by each thread, we use sort of binary search to sort of see where each thread should start and work. The good thing about that binary search is, I mean, technically binary search should be pretty bad, right? Because different threads would take different branches. But the problem is, the good thing is that runs very short. It's not actually running very long. It's like just trying to binary search between a set of vertices for a thread. So it like runs for maybe a couple of iterations and that's fine. Yeah, that it's not a load bearing sort of kernel. Also, it doesn't do that many memory accesses. I mean, it does memory accesses into the array, but those arrays are stored in the shared memory, so the cost of that is pretty low. I'll get to that. I'll explain how that works later. Uh, but yeah, and we will run like profiler on it too to make sure that that's not a culprit of the performance. Okay, let's talk about mapping uh, and why particular these load balance why these accesses are bad. First of all, let's talk about that. Uh, Move this out of the way. This. Okay, so you guys can see my screen, right? Okay. So here's what happened. We have a matrix which has a bunch of rows. Each row has a bunch of non-zeros. I'm going to show them like this in just to say that how many non-zeros it has. But remember, they are scattered all across the row. So yeah, what we have done now is we have assigned, and I'm going to draw a warp like this. So this is T1, T2, T3, uh, T4, and T5. These are like the 5 threads in a warp handling different rows of the matrix. Now imagine what is happening. How are they accessing the memory? This T1 accesses 1, 2, 3, 4, 5. Accesses column 0, or like the address 0, then addresses 1, then 2, then 3. T2 accesses 0, 1, T3 accesses 0, 1, 2, 3, 4, then 0, 1, 0, 1, 2, 3. In this order, like this is time. Uh, Now, if you look at all the accesses each thread does at one cycle, they are not coalesced, which means they're not accessing neighboring memory regions. They are accessing like these are scattered memory locations in memory. They're not exactly the same. They're not next to each other, right? But what if we changed it to so that in this first cycle, thread 1 accesses this, thread 2 accesses this, thread 3 accesses this, and so on and so forth. Like what I want to do is I want different threads in a warp to access basically different edges of the same vertex instead of doing different vertices, and that way they can access memory next to each other. This is like I want warps to cooperatively work on the same memory location. Sorry, cooperatively work on the same vertex instead of working on different vertices. And that's the idea that we're going to implement first to improve our global memory accesses. So I'm going to stop this. I'm going to stop sharing. I'm going to go back to this window capture, display, I'm going to remove the crop. Okay. Okay, so I'm going to keep the original version, by the way, so that we have all the versions next to each other. Uh, and let's see how we can fix this. So I'm going to copy over this, and let's say let's call this version SPMV co-watt, which means all the threads in a watt are going to work cooperatively. Now, I'm going to remove this just so that it's easier to read. But the previous one has it. Okay, so this so far the code is exactly the same. What I'm going to do now is uh, he- we're going to first see for each thread. I'm going to identify which uh, vertex I'm going to work on. So I'm going to launch 32 times the number of threads than the vertices. So the RID is going to be thread ID divided by 32. So if I have 5 vertices, I'm going to launch 32 times 5 the number of threads. So that way I have 32 threads handling each vertex. Now within those, what we are currently doing is each thread starts from the edge number 0 and goes up to the end of those non-zeros and then increases by one by one. But instead of doing that, I'm going to now say start from now I'm also going to complete the lane. Lane is usually a terminology we use to lane ID is to decide is to sort of represent which thread you are in this warp. So that's usually just computed by doing something like this. So if we just like, or modulo, I'm right, saying our code. So it's basically the index of the thread within that warp. So I'm going to say on the lane ID. And now instead of starting from the very first non-zero in that edge, I'm going to start from the lane ID. So the first thread in the warp is going to start from lane ID from the zeroth non-zero. And the second one would start from 1, 2, 3, and so on and so forth. The condition is still going to be the same. All the threads stop when they reach the end of that non-zero, that row. So we don't like go beyond that row. Each thread still handles one particular vertex at a time. And then because we are accessing neighboring rows, so for each thread now, we don't have to necessarily process the next. So if thread 1 is doing the first uh, non-zero and the second one is doing the second one, after we are done with all these 32, we don't have to do like the next non-zero. Now we can hop 32 at a time. So what I'm going to do is I'm going to cdix plus equals to 32. So each warp, like warp number 0 would do 0, 32, 64, 96, and so on and so forth. Thread number 2 in that warp would do 1, 33, 65, and so on. So let me just like maybe write this as comment here. TID or lane ID 1 does 0, 32, 64, 96, 96th non-zero in the row. Lane ID 2 does 1, 33, 65, 97th non-zero in the row. And then this remains exactly the same. This part remains exactly the same. But what benefit did we get out of this? If you look at these a dot d columns now and a dot d values array, this CID X that's being used to index into it, if you think of each lane for a particular cycle, uh, lane 0 is doing 1, lane 2 is doing 2, lane 3 is doing 2, lane 3 is doing 2, lane 4 is doing 3, and so on, which means lanes in the particular warp are doing consecutive memory accesses. They are now handling, they're loading data that's next to each other, which is good. We want that. We want neighbors to load threads in a warp to load consecutive data. The only change we have to do now is to uh, I'm going to keep this so that we have uh, actually no, I'm going to remove this. I'm going to call the co-warp kernel. Um, no, actually, we need to compute the number of rows and number of blocks again. So let's see. So uh, running simple vertex or simple row mapping version, one thread equals one row. Um, then I'm going to do running co-warp version, 32 threads in a warp simultaneously. If I can spell simultaneously, oh God, process a row. So how does this change? The number of blocks remain still the same. So I'm going to say block size equals 512. Then I'm going to say num blocks equals, but I need more threads. I need 32 times the number of threads for each num row. So I'm going to say num rows times 32 plus block size minus 1 divided by block size. Uh, this condition now just becomes, oops, sorry, not this one. This condition needs to be changed to be RID, not PID. So if thread ID is, if RID, the row ID is greater than number of rows, then return. Yeah. And then I'm going to, this remains fine. Read this. This execution time basic. Execution time core. Yes. Let's call the right kernel. Okay. What we called it? Co underscore what? Yeah, co underscore what. Okay. So this one is going to launch 32 times the threads, but then those 32 threads in the warp are cooperatively going to process the non-zeros in a row. Let's see how much performance difference we get out of it. Yeah, let's not run NVVP for now. Let's just run it normally and see if there's a performance difference. Okay, so there is a huge difference. First of all, it went from 0.42 milliseconds to 0.007 milliseconds. Uh, let's and we have asserted correctness of this, so we have a huge improvement here. Let's look at Visual Profiler and see what Visual Profiler says about where does this come from. The one time I don't do it correctly. Okay, so we have two kernels this time. You can see that the SPMV code one takes shorter, it takes 15.2% of the time. But I'm going to examine GPU usage. Let's see if they have any difference in the utilization and the memory accesses first. So, okay, individual kernels, we're going to go one by one through them. So our old one SPMV, we're going to do the normal kernel analysis on it. And let's look at the global memory accesses, which we had seen before. And they are still bad, like we had seen before. Let's look at um, the core kernel. Okay. So this one actually has somewhat better. So you can see this load that we are doing, which goes and fetches the value from the dense vector, is still bad. In fact, it's worse than before. Like because this is still doing random accesses. This is still actually. Let me pull up the code for that if it's easier to see. I'm gonna do this and remove the filter from this. Okay, so there are two. I'm going to just put the thing up so we can see the side by side, but you just need to notice that there are like two different axes and how they behave. So let's see. Yeah, so there are two accesses here. One access into the columns array and the values array. These two are actually pretty good now. Like if you look at these loads, they're decent. They're not too bad. But this load from the d underscore b is awful. Because what is happening is we're using the column index, which is an indirect access to go into it. The memory accesses are not coalesced in this case. This actually is technically very hard to get around just because your non-zeros, it's not like your rows values are blocked. Like it's not like your row values are 1, 2, 3, 4. Your row values are going to be like 5, 13, 15, 16, depending on who the neighbors are of that node. So this is very hard to make it coalesced, at least for now. But what we have managed to do is we have managed to at least make sure that the loads on the column arrays are coalesced. So instead of assigning each thread to a different row, we have assigned 32 threads to each row. And that way we have like made sure that each thread is reading consecutive values. What is the what is the utilization of this kernel? I need to go back. Let's see. This freeze, no. Compute utilization for this new one. It's still bad. It's so SPMV was let's see. Actually, no. Let's look at divergence basically. Uh, Divergent execution. Okay, yeah. So this one has divergence, but it's not as bad anymore. Like it's less than before, but we haven't still solved the problem. The different threads are still handling different number of non-zeros because when you're iterating through the non-zeros in a particular row, you could have say 15 non-zeros, but you still launch 32 threads to handle them, which means they are going to 17 threads are sitting idle, and that's bad for performance. So there's still divergence happening. It's less than before, but that's what load balancing will fix. We will get to that and we'll fix it with load balancing. But for now, what we did is we changed our iteration strategy. Instead of mapping one vertex to a thread, we assigned a bunch of threads in the warp to a particular to a row and handled non-zeros in them correctly. That way, our performance actually went up down from our execution time went down from 42 milliseconds to 0.07 millisecond. Actually, we should do some warm-up runs too, because to make it completely fair. So I'm gonna say no to change the code. I'm going to run more runs first of all, not one. So let's run like 100 runs of both the kernels, and then do at least 10 warm-up runs for each of them. That way we get more accurate numbers. This will take a little bit longer to run now. So basic version runs in 0.224 milliseconds and the higher one runs in 0.191. So yeah, the difference is not as much. I was actually surprised when the distance difference was too high. Yeah, so it has improved performance, but it hasn't improved it that drastically as before. So running in the same warp has performance benefits. Not, I mean, threads are still running in the same warp. It's not like they're running in different warps now. It's just trying to make sure that the threads in the same warp, the threads are organized in the warps. They're not like choosing which warp to run in. Trying to make sure that threads in the same warp do similar things, which means accessing close by memory, doing the same number of iterations. That is important. That is what improves performance. If you make sure that the threads that are close by to each other are doing the same uh, 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 like memory accesses and number of iterations, that improves performance. So what we have done here is basically just improved the performance by uh, coalescing the accesses on the column index array. But the accesses into the vectors is still bad, and we will fix that next. But I think we are closing up to like 2:30 Eastern time. So I guess we will close this here for now. Next week, I mean, whenever next time I stream, I would implement a load balancing strategy called the TM. Let's do WM. So, by the way, let's actually just look at some of the material for that. Uh, So this is one of the papers that we compared against, and it actually motivates a lot of these strategies. So this paper is a really interesting piece of work, by the way. Pattern-based algorithmic autotuner for graph processing on GPUs. This one, the system is called G Switch. But if you actually read through it, if you have some time, just check out this load balancing section of theirs. They talk about different strategies that you can use to load balance the kernels that you're running. The load balance strategy that we'll implement the next time is called the warp mapping strategy. What this basically tries to do is reduces the imbalance in a warp. So it tries to make sure that the threads running in the warp, in the same warp, are doing equal amount of work. So they are processing equal number of non-zeros. That's what we will try to do. Right now, the implementation that we have, each thread will still do different amount of work because it's not guaranteed that the number of non-zeros in a row is exact multiple of 32. And if that's not the case, then you're doing different amount of work. So WM is a strategy what that we'll implement. We will also implement this TWC strategy, which actually handles irregularity in number of non-zeros itself. So if different rows or different vertices in a graph have very different number of non-zeros, we'll handle that by separate implementation. So what TWC method does is it separates the active vertices into low, medium, and high degree vertices. So it sort of splits those vertices into vertices that or rows that have fewer non-zeros, a medium number of non-zeros, and a large number of non-zeros, and then handles them differently. So runs different code for the low ones, the different implementation for or different load balance strategy for the medium ones, and a different for the high degree vertices one. And this is like sort of a hybrid load balance strategy in that sense. We will see, we will implement this one too. And then finally, we will implement a load balance strategy that we have in our paper called edge only load balance strategy, which is basically very simple but very effective for this sort of SPMV application. And then we'll also do some blocking to improve our cache performance. And that at that point, we will see how good or bad our performance is from our current level. Hopefully, it will be much more different. But yeah, going back to our terminal, we reached a point where we implemented basic and co-op, and we got slight performance improvements over like a graph which has 4 million number of non-zeros. Uh, And yeah, next time we improved some performance. We saw in the visual profiler that our performance is improved because we managed to improve some of the global uh, coalesced accesses. So yeah, sorry about the issues with the profiler. I mean, with the kernel not launching before. I will spend some time debugging, and hopefully next time I'll have an answer, not just a working code, just also an answer as to why it was not working properly. Uh, my guess uh, is some version kernel like the driver mismatch with the SDK that I'm using, or I did some indirect like some wrong memory access, which now is correct. I'll figure it out. I'll explore and let you guys know next time what the issue was. Yeah, we unfortunately had to waste an entire hour trying to debug that. But at least we know for sure now that the code is running correctly. Otherwise, this part of the code would complain. This correctness check is making sure that our GPU kernel is doing the right thing. And since this is running correctly, we know you're not doing something wrong. So yeah, that's all for now. I'm gonna push this code. I'm gonna clean. I'm just like save this code, put it in the GitHub repository, and push it. I'll also update the resources doc with the links for this G Switch paper, one of my own paper from the from 2.5 years ago. If you're interested, you can read those. And yeah, and that's all for today. I'll see you folks the next time when we hop on.